first, okay, about that passcode. Okay, how come we have so many passcodes? Okay, it's because I actually asked the department to assign one additional classroom to this class. Okay, so so next time, if you come to this class and you cannot find a seat, okay, you can go to the A203, okay, A203, okay. But you have to bring your computer with you because we are going to make this class like kind of like streaming, okay, like maybe YouTube streaming， 变那个 YouTube 直播之类的 ，OK， 所以 so I will become like a 网红 something like that. Okay, yeah, so 那个遥控器在哪边？这个Well, it doesn't work. Okay, so but consider like I don't take attendance. So the good news is that like after the first class, I think like a lot of students will not come. So we should be able to go with this classroom. Okay, I mean after I still prefer like you guys like to have like a face-to-face lecture. Okay, so let's get started. Okay, so this is the first handout. I think I have the student to print my TA to print like enough content for you guys like for at least for today's class. Okay, and as I said when I went through the syllabus, after this class, okay, if you need additional handout, I will make sure all the handout, all necessary handout be available on eClass to download at least a week prior to my class. Okay, so but you need to do it yourself. Okay, we are not going to print additional handout for you because, well, it's not like everybody needs like a printout handout anyway, right? A lot of students just use like a PDF file to read it like on the computer directly anyway. Okay, so anyway, just want you guys to be aware. Okay, so to download the handout yourself. Okay, next time. So this class, okay, we are trying to use the data to solve the problem. Okay, so in computer science, okay, the traditional approach for problem solving, okay, is that, okay, you have a problem, okay, so you have a good look at the problem and you study on that problem, and then, okay, based on your understanding with the problem, you write rules, okay, and use those rules to solve the problem. Okay, so obviously the rules you used, okay, I mean once you make it a program, okay, you are able to evaluate, okay, I mean your program, if it runs well, okay, if it solves your problem, I mean everything's great, okay, you just launch it, okay, without any problem. But if there's any issue, okay, with the solution, okay, it means something's wrong with your rules, which obviously should go back to your problem understanding. So you have to analyze the error and then find you know, most of the time, I mean, it should give you better understanding of the problem. So you probably will have to write, you know, to revise your rules, okay, revise your rules, and eventually, okay, write a second version, okay, and then you evaluate that, okay. Basically, this is a loop, okay. You keep doing that until your problem gets resolved, okay. So obviously, okay, in this process, okay, this traditional approach require a lot of manual work, okay. I mean, we humans have to involve in a lot of, you know, I mean, a lot of places in this process. For example, study a problem, obviously, is done by the human, okay? And the evaluation, once you have some error, okay, the analyze the error part, obviously, is done by human too, okay? And, you know, from the problem study to coming up the rules, normally, it's, this is also done by the human. So this process, like, you know, it's, even though it's a traditional approach, you know, it is not ideal. It's not ideal. Okay, so when machine learning come into play, okay, you still study the problem, okay, and then based on your idea, okay, you are going to train a machine learning algorithm, okay, and so you can see that the whole process, okay, is kind of similar to the previous one, right? It is because, okay, in machine learning area, okay, here, okay, I'm not talking about deep learning, okay. So you may ask, what is the difference between machine learning and deep learning? Okay, to be honest with you, okay, a lot of places they consider deep learning as a part of machine learning, okay. But now I'm trying to, you know, when I refer to machine learning here, I'm trying not to refer to deep learning, okay? Because the traditional machine learning does not require so much data, okay? I mean, you can, for example, like in a traditional machine learning, okay, a lot of algorithms perhaps require only like, you know, hundreds of entries of data, or at most thousands of data, and you are able to have a pretty satisfactory result, okay? But obviously in deep learning, you require much more than that, okay? So in the machine learning, as I said, okay, you don't have that much data, okay? So you still study the problem, because the data, as I said, I mean, it's not a lot, so you normally cannot, you know, cannot study the just the data. You have to study the problem itself, okay? And then based on the property of the problem, as well as maybe the small amount of data that you have at hand, you decide like which algorithm to use, okay, which machine learning algorithm to use. But you can see that, okay, this process, okay, still like there's a lot of manual work, okay, and it's difficult to automate, okay, it's difficult to make the whole process like, you know, to, I mean, as less human involvement as much, okay. So now, okay, one way to do it is that, okay, here, okay, the machine learning that automatically adapts to change is like, now we have a lot of data, okay. This is more like deep learning stuff, okay. So from the data, the problem is actually defined by the data directly, okay. And then you basically like, you can use the data to train your algorithm, okay. So in this scenario, pretty much you have a lot of data. So a lot of time, the machine learning algorithm that you use, okay, can be like a deep learning, okay. and then you evaluate the solution. Okay, if it's good, you launch it. Okay, and because the algorithm, the solution is normally comes directly from the data. Okay, normally it's not going to be an issue for the current data because data itself is the problem, right? But obviously, data could change, right? You may collect more data, or the data may be obsolete, okay, in the future, okay. So if the data gets updated, I mean, you may need to go through the whole process again. But this whole process does not require a human to analyze the problem anymore, okay. So this whole process can be automated much better than the traditional or like the previous schema. Okay, so this is something we would like to achieve. Actually, okay, not only that, okay, with lots of data, okay, we even expect the machine learning or deep learning algorithm to teach us the property of some problems. Okay, so because I mean you have lots of data, so you are able to have train the algorithm to solve this problem, and from this solution, okay, we human can inspect the solution and get a better understanding of the problem. Okay, and then so this is like the machine learning actually is used to help us human to understand the problem because as I say, like the problem actually, I mean, is now defined by a lot of data, but it's not well defined. Okay, a lot of time, I mean, this type of problem is not well defined, so it's very difficult to study a problem directly. Okay, instead you use this data to derive algorithm, and then use the solution to help you to understand the original problem. Okay, let me use one example. Okay, you guys know AlphaGo, right? AlphaGo is one of the well-known example about deep learning, right? I mean, it has been used to beat the professional like Go players, okay, and we know like how difficult the Go game is, right? So, I mean, now like in Japan, like every time they play like professional Go games, okay, like Minren or like Qixen, okay. I mean, every title game, basically there's like how should I say, like kind of like the AI score behind like the player. So every time a player plays one move, okay, the score actually gets changed. So basically you can sort of consider like that's like one way to evaluate how good that player's move is. Okay, I mean, in the traditional Go area, normally, I mean, we cannot like judge a move so easily. Okay, we need to start. I mean, a lot of professional Go players need to study the move, like spend so much time to understand the move. But now, okay, with that simple score, we can sort of very easily to understand, like, oh, this move is extremely bad, or this move is like well, it's relatively okay, something like that. So that actually that machine learning or like deep learning model, okay, behind the game actually is used to help us human to understand the Go game much better. Okay, because I play Go games, okay, myself. I'm an amateur 1D, okay, amateur 1D. If any of you like to play Go games, okay, let me know, okay. Maybe if you beat me, okay, you get some points, okay. Yeah, just kidding, yeah. Okay, so that's but even though the machine learning or like deep learning, I mean, in this class, okay, that we are talking about, okay, I mean, it's good, okay, as I already mentioned, it's a benefit to us, but machine learning or deep learning is hard, okay, why? Okay, here I list a number of issues, okay, for the machine learning. The first part, okay, is about data, okay. Is your data, okay, are your data representative to this problem that you are studying, okay? So representativeness of your data is important, okay? For example, okay, sometimes when you collect the data, okay, you may correct like wrong samples. So for example, okay, let me, because recently, like I think like at the end of this, before the end of this this year or early next year, we will have an election, right? In Taiwan. Okay, so if you go, I mean, if you you know turn on the like a TV, like there's a lot of like a program like debating like okay, which candidate is good, which candidate is bad, something like that, right? Okay, so you know like a certain channel is maybe pro certain like a party, right? Okay, so I mean the you know the study, okay, that is done by certain channel, okay, may have bias. We know that, right? So maybe they will ask like, okay, if the channel will ask, if you support particular candidate, please call in. If you support the other candidate, please call in. And different channel will get totally different results, right? Okay, so maybe like this channel is good, is favor, it's more like a DPP, preferred. So it will get like a, you know, the DPP supporters will tend to call into that channel, will tend to watch that channel. The other channel maybe like it favor KMT candidates, so it will get more calling from the KMT supporters, right? So you can see that, okay, different channels will have very different results, okay? I mean, they both collect data, right? They both collect data, but their data may not be representative for the current situation, okay? So that's the issue, okay? And another problem is the data balance, okay? This is especially a problem in the classification, okay? For example, if you want to design have a model that do like classifications, okay? Say we want to have a model that determine if a vehicle is going to, you know, trespass like a red light, okay, 闯红灯啊, okay, it's going to like go just drive through the red light, okay. You want to classify that this type of vehicle, I mean, to be like okay, this vehicle is not going to, it's going to stop for this red light, or this vehicle is going to you know, it's not going to stop for this red light, okay. When you collect the data for analysis, obviously you are going to collect, well, I'm assuming like Taiwan citizens are, most of them are abiding the law, right? Abide by the law, okay? So most of the drivers will stop for the red light, right? So you are going to collect very few sample, very, very tiny sample that will not stop for the red light, right? So maybe the ratio is like 100, in 100 drivers, only one of them is not going to stop for the red light, Okay, so 99% of the drivers will stop for red light. Okay, so if you use that data to train the model is going to tell you, okay, oh, no matter which driver drives the vehicle, okay, the model is going to tell you, okay, he's going to stop for red light. Why? Because if the model predict like that, it has 99% of accuracy, right? The model is smart, okay? The model is smart because from the data you feed to it, it derives that, okay, just directly predicting the vehicle will stop for red light gets the highest accuracy anyway, right? So it's not going to learn any particular feature whether this car is not going to stop for red light. Well, it doesn't matter. It just predict this car is going to stop. Okay, so the reason for this, okay, is because your data that you collected is very unbalanced, maybe like a 99 versus 1. Okay, so that's the problem. Okay, so of course for each of these problems we have a way to deal with that. Okay, and also we have so many different machine learning algorithms out there. Okay, here, okay, if you are talking about machine learning algorithms, there are so many out there. Okay, but even for deep learning, we have many different approaches. Okay, as we will discuss in the future. Okay, so which algorithm do we use? Okay, and there are some algorithms that tend to have higher accuracy, but there are some algorithms that can give you better interpretability. Okay, you can explain why this model make this decision much better in certain model. Okay, so which consideration do you have? Okay, when it matters when you select like the machine learning algorithm. Okay, and also like which feature should you use? Okay, to train the model. Okay, for one problem you may collect so many features. Okay, but you may not use all the features. Sometimes you will find that using only part of the features is actually better than using all the features. This is true. I mean, a lot of time. Okay, so which features to select? Okay, is an important issue, feature selection, and we also have like a consideration for example, such as optimizers. Okay, what optimizers to use? Okay, I mean, I will explain optimizer. I mean, later. Okay, in this class. Okay, we have so many different optimizers. Okay, sorry. Here, I mean, I'm talking about the cost function. Okay, cost function. It could be MSE. It could be entry, the binary cross entropy. Okay, something like that. Okay, depending on your problem, nature of the problem. Okay, and do you want your solution online solution or offline solution? That's also, I mean, the consideration that you may have, I mean, in machine learning algorithm determinations. Okay, and in terms of model performance, okay, you also need to consider, for example, okay, when you tune the model for better performance, okay, is your model underfitting or overfitting? Okay, if you don't know the term underfitting, overfitting, I will explain quickly. Okay, but of course, like if you in the machine learning class, I mean, they will probably spend more time, okay, to explain that. Okay, we are only going to spend, I mean, very short period of time to do that. Okay, and there's a trade-off between false positive and false negative. Okay, so what I mean, if you want to optimize false positive, I mean, you want to reduce false positive, normally the false negative will increase. If you want to reduce false negative, false positive normally will increase. Okay, but in some applications, false positive is important. Okay, you don't want false positive. In some application, you don't want the false negative. Depending on your application, you may want to get rid one of them. Okay, but if these two are both bad, then you need to find a balance. Okay, a perfect balance to reduce both terms. Okay, so these considerations, okay, make the machine learning difficult. Okay. So in this class, our focus, okay, as I said, there are so many different machine learning algorithms, but we are only going to focus on the deep learning area, okay, which is like a much more popular branch in machine learning in recent history, okay, and we want to emphasize on the hand-on experience, in the sense that I want you guys to to not to focus that much on just the concept, but also focus on the writing codes. Okay, play with the algorithms. Okay, that is the reason you can see that this class, the only written part requirement is the final exam. We don't have any homework. Okay, everything else will be project based. Okay, I want you guys to work on the coding. Okay, so this is the hands-on experience is what I emphasize in this class. So, well, let's take 10 minutes break. When we come back, we will continue, okay? Yeah. The textbook, okay, is this one, but I have a couple of references for you, okay? The first one is Deep Learning by Goodfellow, Yoshua Bengio, and Aaron Kurzweil, okay? These two guys, Ian Goodfellow and Yoshua Bengio, they are recipients of a Turing Award, okay, because of their contribution to deep learning, okay? So this book is like considered as a Bible for deep learning area. But the reason I do not want to use this book is because this book is very, very theoretical. It doesn't even talk about program at all. Okay, I don't think we want to go that much theoretical. Okay, so that's why I don't use this book. Okay, but obviously, if you want to dig into the foundation of deep learning, this book is a very good one. Okay, and because we are using Keras, so this is also one of the Bible for Keras. Okay, because this deep learning with Python. Okay, this guy, Francois Collat. Okay, he's like the inventor of Keras. Okay, so his this book obviously is about Keras. Okay, so this book, by the way, is freely available online as a PDF file. Okay, so you can download it and read it. I mean, relatively easy. Okay, but to be honest, okay, beginning close to the end of last semester, okay, I wanted to switch to PyTorch. Okay, I wanted to switch to PyTorch. I even already prepared a textbook. Okay, this was the textbook I prepared for the PyTorch. Okay, and even though we will cover Keras in this class, I mean, I have no problem you guys use PyTorch. Okay, because after all, PyTorch has been much more dominant in the academia area. Okay, so um, the I would say the fighting between Keras and the PyTorch is the verdict is that PyTorch is leading, at least. I would say the verdict is PyTorch is leading. So if you want to learn PyTorch, okay, the third book is a good one. Okay, again, you probably can find this book online. Okay, but I cannot tell you where. Okay, and at the end, I didn't do the switching. Okay, it's because like thanks to my master student, like I spent the whole summer, like almost whole summer working on their thesis. Okay, so I didn't have time to really like get into like this thing. Okay, if I want to do the switching, I will have to revise the whole set of slides. So it's a lot of work. Okay, I'm sure I will do that maybe next year. Okay, I'll switch to PyTorch next year. Okay, so but if you want to do it now, okay, the third book and the fourth one should be good reading. The fourth one is a book I think it's very good, but this guy, okay, I think this guy is pretty good. Okay, the author of this book, okay, this one, Edo Drori, okay, he's a professor at Boston University and MIT, okay, and also I remember Columbia University, okay, so he has joint appointment at these three universities, okay, and he wrote this book, but you can see that when will this book be available? November of this year, so it's not available yet. Okay, it will be available maybe in another 2 months. Okay, so when this book come out, okay, another reason I don't want to switch to PyTorch that quick is because this book is not yet available. Okay, when this book comes out, I will survey it and decide like I will use this book or that one. Okay, so but obviously I list them all as like references for you guys. I mean, in case you want to switch to PyTorch, or you could use the third book, and the fourth one, okay, is should be a very good reference when it is published. It's not yet published, okay, but it will be in 2 months. Okay. So, okay. So we are still sticking to Keras. Okay. So I probably want to give like a couple of reasons why we use Keras. Okay. So Keras is a high-level deep learning API, which allows you to easily build, train, evaluate, and execute all sorts of neural network. Okay. So its documentation is available here. Okay. Keras.io. Okay. The reference implementation, also called Keras, was developed by, as I said, Francois Collet. Okay, the author of one of the references, right? Okay, as a part of his own research project, and it was released as open source in 2015. So there's a one period of time, I think, around from 2016 to 2017, 18, this 2-3 years. Okay, the Keras is pretty much dominant. Okay, pretty much dominant. It quickly gained popularity owing to its ease of use, flexibility, and beautiful design. Okay, but around, I mean, after it really, when Keras was out, it didn't have any competitor until Facebook came out with PyTorch. Okay, so at present, okay, you can choose from 3 popular open source deep learning libraries: TensorFlow, Microsoft Cognitive Toolkit, okay, CNTK, and the Thanos. So to avoid any confusion, we will refer to this implementation as multi-back-end Keras, okay. So Keras actually has two versions, okay. Since late 2016, okay, other implementations have been released, okay. So you can now run Keras on many platforms. After all, as I said, very dominant. So almost all platforms support Keras, such as like Apache, MXNet, Apple Core ML, Java, JavaScript, TypeScript, okay, and Plate ML. Okay, this Plate ML is an open source movement to use GPU other than just the CPU. Okay, so for example, if you have AMD, okay, AMD also has its own GPU, okay, not just NVIDIA, right? So we use, for example, so they all have they all support Keras. Okay. So TensorFlow also it's a 2.0 version. It now comes bundled with its own Keras implementation. Okay. I just want you guys to understand. TensorFlow used to be, it was actually supported by Google. Okay, the giant behind TensorFlow, and again, Google consider Keras a very easy to API. So it actually includes the Keras in its 2.0 TensorFlow 2.0 version. Okay, so only support TensorFlow and backend. So it has eventually offered some very useful extra features. Both TensorFlow, data API, but unfortunately, I think in this class we are not going to cover data API. Data API is we don't have that much. Okay. The code example. It should run fine on other Keras. In the class that we are discussing, it should run fine on other Keras implementation as well. But with only minor modifications, such as changing the import. So the import, like the path, may be slightly different. Okay. So if we try to put it in one picture with something like this, okay, so you can see the traditional Keras, okay, we sit on top of different samples, okay. So we call that multi-backend Keras, okay. And now, as I said, TensorFlow 2.0 has its own bundled Keras, okay. It's TM dot Keras, okay. So basically, this Keras, okay, every code you run, okay, should pretty much work on this one or this one, okay. But we only exception that the import and the path may be slightly different. Because this one you have TM dot in front of Keras. The other one is starting with not, okay. But this is the thing that we are going to use. So, Keras is very cycle. Okay. In the current, if you go to like GitHub, okay, you see like different deep learning open source. Okay, you will find that currently the majority of the
top. Use PyTorch to debug the code. Okay. But Keras is the second most popular. Okay. The ratio is probably 2 to 1. Okay. In the past, they were very close. They were very close. But now, I think the PyTorch is winning. Okay. That is also the reason I told you. I want to try to convert this course to PyTorch. To be honest, this competition is close. I have at the very beginning when I offered this course 2 years ago. Okay, because at that time we only have TensorFlow version 1, so I was teaching TensorFlow at that time. So after TensorFlow 2.0 came out, because as I told you, TensorFlow 2.0 support Keras. Keras became very popular, so I had to switch to Keras. But now it looks like I have to do the first switch, but probably not this semester, but next. Okay, I just want you guys to be aware. Okay, even though this class we are teaching Keras, but you guys are much more welcome to Python. Okay, in your project. Okay, so the most popular deep learning library after Keras and TensorFlow is basically Python. I mean, you can understand why Google doesn't use Python. Okay, it's because that it's messy. Okay, it's basically is behind PyTorch. But the guy, okay, who is in charge of PyTorch, okay, development is Yang Chong, okay, who is also one of the recipients of the deep learning contribution Turing Award. Okay. So I think that Yang Chong we are going to talk about him. I think quite often in this class because he has done so many contributions to this application. The good news is that its API is quite similar to Keras. So PyTorch and the Keras, they are very, very similar. Okay? As long as you know how to use Python. Okay. If you know Keras, it's not very difficult to pick up Python. If you know Python, it's not difficult to pick up Keras either. Okay. To be honest, if you ask me which one is easier to learn, I probably will tell you it should be Python. Because if you know Python, Python is actually closer in terms of syntax to Python. Okay. So that's probably the reason Python. Okay. But as I said, they are very different. Okay. And second, PyTorch popularity grew exponentially in 2018. So as I said, when Keras came out in 2015, it gained very, it was a big hit in 2017. But PyTorch, when it came out in 2018, it became very popular. And now, after a couple of years, PyTorch. So the reason for PyTorch to become so popular is because it's basically an excellent application. Okay. In the past, this was the reason of the PyTorch. After the Keras, this was the reason of the Keras. The documentation actually not that good. Okay? But the PyTorch documentation from the beginning was but now, after Google integrates the Keras into its TensorFlow, okay, Google obviously is a big company, right? So they spend a great amount of effort to rewrite the documentation for Keras. Okay, so for documentation, okay, has also been completely removed, and it is much easier to find what you need now, okay, for Keras. Okay, so the benefit of documentation for PyTorch is not so much now, okay, and Keras has improved this documentation. Okay. So PyTorch main reason, okay, such as limited portability and no computation graph analysis, okay, have been, largely addressed in PyTorch 1.0. Okay. But PyTorch 1.0 is not the first version. The first version of PyTorch is PyTorch 0.9. If you ask me why 0.9 is the first version, I cannot give you an answer. Okay, I don't know why. But the PyTorch new version is called PyTorch 1.0. Okay, so PyTorch 1.0 also improved. So, after this reason, okay, this reason. Okay, so this is like health competition is beneficial to everyone. So, okay, in this class, okay, we are going to do Python 3, okay, with the Keras. So there are many Python distributions, such as CPython, ActivePython, PyPy, one to support different platforms such as Windows, Mac OS, Linux, and it comes with many IDEs, okay, including Jupyter. I think Jupyter is primarily IDE that we are going to use. Okay, if we use Jupyter for a while, at the beginning it will not be that great, okay, but having to use it for a while, we will have it. So it is optimized for that level. That is the primary reason they choose the format over our solution. So you can download it from this place. Okay? And make sure you choose the one with Python 3 form. Okay? The latest version should have worked. So since we are using Python 3, okay, if you are not that familiar with Python 3, okay, there's a Python 3 tutorial here, okay, for you to take a look. So I will not go over Python 3 in this class. Okay, I hope that the majority of you should original Python, right? But if you don't know Python, okay, so this is the place you should go to, okay, to quickly get that. Okay. So for those who are familiar with Python version 2, okay, but not Python 3, okay, the following link should be helpful. Okay. This one tells you the difference between Python 2 and Python 3, the key difference. Okay. So just want to make sure you guys have a place to basically catch up with Python. So in the following, okay, a couple of slides, I basically try to tell you how you will set up your development environment, okay, for this class. But I think I will skip those. You guys can follow this setup your computer. In this class, I actually encourage you guys to bring your computer to the class. Okay? And you should be able to find the source code of this textbook. Okay? And this author has all the source code of the textbook there. field, so you can try to test social. So we are talking about class, which is big time. Okay. But the environment setup, I think that without computer to go through that use search. Okay. So I would just expect you guys to do it by yourself. To be honest with you, okay, I think this covers right. This is the Jupiter interface. This is the whole space in Jupiter. Okay. After this, follow the instruction to set up the environment, you will have the Jupiter. That is very convenient for your development. But to be honest, okay, the Google actually has like they provide like a free CPU environment to use. Okay, provide that. Okay. Yeah. It's something like this. Okay, so it is also like in Python, in Jupyter format. Okay, and it allows you to write your code and run to train your model. Okay, as long as you don't use that much CPU. Okay, so it's nice. It's pretty nice. Okay. I think for this class, that Colab should be good enough. Google Colab should be good enough. And you don't even need to install anything. Okay, just use the browser. Okay, point to the right place and use the environment. Okay, so which is, as I say, it's a very nice resource to use. Okay, and also obviously, because it's supported by people, obviously the TensorFlow. Okay, so basically, if you use that approach, you don't need to worry about the installation stuff at all. Okay, you just use the code. Okay, so yeah, obviously you don't use the tool on your computer. You use code. Okay, but I did have a Colab instruction, but you can search Google Colab, and find it. Okay, so we do have 30 minutes. Okay, so first, let's try to use the example to talk about linear regression. Okay, let's talk about linear regression. Linear regression model is a linear model that can be used to make a prediction by computing a weighted sum of input from the concept. Okay, this concept is what we call it bias, okay, or intercept. Okay, so it's something like this. In here, in this equation, okay, the theta 0 is the constant or bias or intercept that I was referring to. Theta 1, theta 2, theta 3, theta 4, up to theta n are the weight for x1, x2, x3, x4, from 1 to xn. Okay, in which, okay, xi are the features, okay, and this y hat is the predicted value. Okay? It's not a real value, it's a predicted value. Okay, so this is obviously a linear function, right? So that is why this model for the linear regression. Okay, so we can rewrite it into a much more easier form, like this. Y hat equal to h theta h. Okay, equal to theta p dot x. Okay, in here, okay, theta p is theta 0, theta 1, theta equal to okay, this vector, that is transport. Actually, if you don't do anything, the theta is just like this. Okay, so theta p is the transport, so it becomes like this, right? Okay, you know that, right? So the x in this in here, okay, is the x is like this. 1 x 1 x 2 we have a 1 especially here. Okay, so this is theta, this is x. So theta transpose, okay, dot x, okay, it becomes like this one, this is like a metric multiplication. You know how to do that, right? So it will become like this, right? Okay, so we should use this on the field. Okay. So when you write like this, okay, it looks much simplified compared with the top format. And yeah. So you can consider it as a function for vector x. Okay, so we call that h theta, but actually it's a theta p times x. So if you have a bunch of data points, then you want to find the set of sets. You want to find when you are given a bunch of x, I, y, I, okay, data points. Okay, you want to find this one, this set. Okay, the weight is weight such that okay, when you plot your x, okay, the y hat and the real y will be close. Okay, because you want to find a linear regression model for all these points. Okay, so it's going to be something like this. Okay, you have function points. Each point obviously is x, y, z. Okay, well, here we have x and we have more than one dimension, right? But let's try to simplify the x to only one x. Okay, then your point will have x and y, right? So when you have this x and y, okay, you want to find your weight, okay? When I say weight, it includes theta, it includes the human cell, body, and theta, right? Because we only have one x, right? So we don't have the other part. So we have theta, going up and theta 0 to theta 1, such that, okay, you target your x, okay, into the function, okay, the value you are going to get, okay, the difference between y and y hat will be, the sum of all these things, okay, will be as small as possible. Okay, so this is like we call it linear regression model. Okay, and if we consider, okay, remember I said that the cost of around midnight, okay, the error, right? I mean the error, okay, if we consider the error to be higher than around midnight higher than sum all that together and divided by n. That's it. Okay? Because n is a fixed value. Okay? When you have n number of points, n is fixed value. So pretty much this difference pretty much determines how big is MSE or RMSE. Because pretty much, okay, mathematical species, we could derive a closed form solution for that, okay, which is this. Remember, we want to find a set to minimize this, right? So then theoretically we can get it directly here. Okay. X transform times X. I mean the inverse of this. Okay. Times X transform times Y. Okay. So the second line. So this will give you set of points. Set of points will be the value set that minimizes cost function. Okay? As for the proof of this closed form derivation, please check out this thing. I will not have time to go through this. First, this class is not about linear integration. Second, I think that pretty these two proofs, okay, this one is much more shorter proof. This one is more prefer the more complete proof. Okay, and so we have this. So which is good, right? We can theoretically prove that this set, this wave, the set of waves, will give us the minimum cost for this cost function. So, but there's one issue. Okay, which is the computation on that. Okay, how much time does it take to compute this data function? Okay, here, okay, remember we have many data points, right? We have many data points. So this x is like this, right? X is like this, right? And of course, in real situation, as I explained, if you have n points, you have x1, x2, x3, up to xn, all these values there, okay? And obviously, for y you have for boundary y, okay? Y is y1, y2, y2. So something like this. So you have this all these values. Okay. So this is graph is n, right? You have n. This n cross plus. Okay. We want to make it very accurate. It's n cross plus. By dropping n, right? So n, okay. Then we do like transpose. Okay. If I remember correctly, this one should give us n times 1. This one should give us 1 times n. So this multiplication will give us n times this matrix. This matrix, the inverse of this matrix, okay, the inverse of n times n matrix, how much time is it to compute the inverse of n times n matrix? Yeah? It's squared, it's more than that. It's about okay. You can optimize the computation a little bit, but it's higher than n squared. Okay, between n squared to n cubed. Okay. Let's say that if you use the Okay, and then you times this one. This one is n times one. Okay, so this one times this one. Okay, it's the n cube for this, and divided by this, it doesn't take as much, and then times this one. Okay, so eventually this one will give you n times one. So look at that. Okay, the whole computation cost is big O n cube, where n is number of points, right? N is number of points. Okay, here, okay, we can even write a program. Okay, here we write it to intentionally generate 100 random points in between 0 and 2. In between 0 and 2. Okay, in the range of in the X range of 0 and 2. Okay, we generate 100 random points, and then we plot it here. Okay, it's basically 4 plus 3x. This is like the linear function. Okay, we try to create a point to run this linear line. Okay, and we put this plot this result in this form. Okay, and the result will be add some random. Okay, so we use that this 100 points and plug it to the this equation. Okay. As you can see that, okay, here, even though it looks like kind of like a delivery company, but it is exactly like, for example, the inverse is the inverse. We try to find the inverse of the matrix. Okay, which is this one, right? We need to find the inverse of the matrix. So basically, we just use the Python code to implement that closed form solution to compute the set of that. Okay, the set weighted weight. Okay, so and then we print out this weight, which is this one. Okay, we try to draw it on the figure. Well, I mean, ideally, 4 plus 3, it should be 3x plus or 4, but it's not, because it's not exactly 3x plus 4. This 2.7 is not exactly 3, right? It is 4.21 something, it's not exactly 4, but well, let's look at the random number, random number, so, which makes it not exactly 3. So you draw it like that. Okay. So you can use this linear function to make you can have a new x value, and you can use this linear function into y hat. Then y hat is going to be your prediction. And ideally speaking, that the best you could have for a linear equation. Okay. And so if you use scikit-learn to perform linear regression, okay, in scikit-learn, okay, by the way, if you have not taken the machine learning class, if you have taken the machine learning class, very likely you already know what scikit-learn is. If you have not taken the machine learning class, let me tell you, scikit-learn is by far the most popular machine learning API algorithm. Okay, it is also Python based. Okay, if you take the machine learning class, I will not say you must do scikit-learn, but I would say that it's a very high part. Yes, they are very huge. Scikit-learn. By the way, I told you guys that the technique we are using actually include machine learning, right? So in the machine learning part, okay, of our textbook, we also teach that. Okay. So I mean, obviously, the Scikit also has linear regression model. Okay, so you can just call linear with IEC.T. Okay, we target the X and the Y, all those points, and we can will tell you exactly the fast width. And you can see this fast width is the same as the close what you get from those code, right? Okay, but let me put it in, let me remind you, okay, this linear regression function, okay, this fitting function, okay, provided by the Scikit, it actually does not use that close one. We try to use something else to compute. Okay, and it's based on SciPy dot lin r LFTFT function. So the name stands for the least width. Okay, so we try to use the least width approach to do it. And the least width to compute the fast width. Okay, it's going to be cheaper than the closed one in terms of capacity. Okay, so this function computes this one theta prime by this one, where x prime is pseudo inverse of x. Okay, it's called a more error inverse. Okay, so you can try to, if you don't know what it is, that's fine. But I just want to emphasize, okay, in machine learning approach, okay, like they use a clever way to compute this weight, which you can get it cheaper, okay. But okay, as I said, there's no more equation to compute. Inverse is, which is like so, the computation of this cost is equal n to the power 2.4, n power 2.4, n power 2. So, okay. So, in other words, if you double the number of features, you multiply the computation time by this one. Okay. So, the power from 5.3 times to 8 times lower. So it takes much more time. Okay. So the SVD approach is used by Scikit, okay, the second approach. Linear regression like that. It's about n squared. Okay. So if you double the number of features, okay, then the computation time is roughly 4 times. So this one is a clever way to compute the optimal way, which will be fast actually. Okay. So once we have trained the linear regression, okay, then the predictions are very fast because it's a linear function, right? So then, so in other words, making predictions on twice as many instances, okay, will take basically twice as much time. Okay, so this is the linear function. Okay. So this is about mathematical closed solution and machine learning approach. But if we try to use polynomial gradient descent, then we are able to get the result. Okay. You could say it's faster, okay, but it depends on how many iterations we are talking about, okay. But in general, the number of iterations doesn't mean a lot to get a very good value. Okay. But I think I'm running out of time there. So we are going to talk about the gradient descent next for coming, and I'll see you next week. Okay?
Sorry for the delay. Okay. Yeah. I mean, so first, I mean, one thing to announce. Okay, the first project. I mean, as I have promised to you guys, I mean, has been uploaded on EE class. Okay, so please, you know, go check it out if you have not, you know, downloaded. And the one thing also to remind you guys is that the TA has also prepared a sign-up sheet for you to, you know, as I told you, like you guys need to find a partner, okay, to form a team for the projects, for the small projects. Remember? So there's a sign-up sheet, okay, the TA has prepared for you to let us know, like, I mean, your team, who will be your team, okay? And I expect, okay, this team information collection will be done in 2 weeks, okay? Meaning, by the end of next week. Okay, next week. Just want you guys to be aware. Okay, next week I will not be. There will be no class next week. You guys know that, right? I already told you guys I will be in Vienna for student recruitment. So that week, I mean, we will not have class. Okay, so but you guys are expected to tell us your team information before the end of next week. I think that's plenty of time for you to find your teammate, right? Okay. So next week is going to be what? End of next week. Let me check. Today is 22nd, right? End of next week. So it's going to be October, let's set it to be October 7th, Friday. Will it be okay? Friday, okay, before the next Friday, okay, October 7th, at least before the midnight, you guys need to let us know your team information because you guys need to work together for the project. Okay, and the first project has already announced. Okay, if you have not found your teammate before October 7th, okay, starting that weekend, the TA is going to randomly assign a teammate for you. Okay, and as I said, okay, it's not a good approach because. Well, some students never do anything for the project, you know. So if you don't want to do everything by yourself, I mean, I suggest you find your teammate by yourself, okay? So, okay, so last week, okay, we talked about linear regression, right? I show you 2 different ways to do that. Okay, one way takes n squared. Okay, n to the power of 2.6 to 2.4, n to the power of 2.4 to n to the power of 3. Okay, to get it done. Okay, it's called like. There's a closed form, okay, called the normal equation that given like a set of, a set of n data set, okay, a set of n data entries, okay, if you have n features, okay, then you can solve, inverse matrix, and to get this, get the optimal linear regression equation done, okay, with this time complexity. And the other approach, is to use a scikit-learn linear regression class, okay, which get your best result, okay, best linear regression, okay, in a time complexity n squared, which is better than the normal equation closed form. But as I said, okay, these two solutions they have like a they are dependent to the number of features, okay. Although like in our example, we only have like one feature, to be honest, okay. But in reality, okay, in many research problems, there are many features out there, okay. Just for one question, actually, like in the first homework, okay, if you observe it, you will see like there are several features, okay, which is actually common, okay, in many data science questions. So, okay, so when this solution, okay, has like a higher order of to a number of features, it's probably not good. It's an indication that they are not a good solution. Okay, so here we are trying to tell you another solution called gradient descent. Okay, which actually the reason I introduced like linear regression is really like linear regression is actually a solution or like it's an algorithm in machine learning. Okay. And I told you I'm going to review some topic in machine learning, which will be beneficial. For you to learn deep learning. But really, like teaching linear regression is really not the the reason for for that. Okay, the reason I want to bring up linear regression is because one method that compare with linear regression, this gradient descent, is the concept that you are going to see it appear so often in deep learning. Okay, so which is the reason I introduced linear regression. Okay, so what is gradient descent? Okay, it's a very generic optimization algorithm. Okay, which is used to find the optimal solution in the wide range of problems. Okay, the gradient descent is actually very simple. Okay, the general idea, just to tweak parameters iteratively to find the the place that give you the minimal cost function. Okay, so for any optimization problem, you normally will have a cost function, and you want to normally minimize that cost function. Okay, so if you try to visualize the cost function with like geometrically, visualize it. Try to visualize in a three-dimensional or like a two-dimensional situation. You have x1, x2, and then the cost will be your third dimension, right? Okay, then it's going to be some kind of like a surface, right? It's going to be some kind of surface, and normally, when we say we want to find the place that give you the minimal value of the cost function, what we are really want to do, is for that surface, we want to find the lowest, the lowest place of the surface, and so The idea is so simple, okay? So basically, okay, because it's once you consider that as a surface, okay, obviously, I mean, because like, let me put it this way, okay? Most of the cost functions, they are continuous and they are differentiable, okay, meaning they are smooth, right? They are smooth. So you can sort of imagine it as like really just like some kind of like a curved surface, okay? So no matter where you go, okay, no matter where you are, okay, imagine you are a ball, okay? You are a ball, and you put yourself at any location, and because it's the surface has like a slope, right? Okay, because I mean, as I say, the curved surface has slope, right? So that slope will naturally bring that ball, okay, to the lowest position, right? Okay, it's kind of just like I mean, you just roll a ball on the ground, and the ball eventually will stop at the lowest place, right? Everybody know that, right? Well, it's a basic physics, right? Okay, so the gradient descent is doing exactly just like that. Exactly just like that, okay? So, okay, the gradient descent, first it measures local gradient of the error function, okay, with regards to the parameter vector theta. Okay, so this gradient actually tells us where to go to find a lower direction. Okay, the direction to go down, basically. Okay, that gradient this is a vector that just tell you which direction will go. You should that ball should go. Okay, to reach like a lower position. Okay, so it goes in the direction of descending gradient. Okay, descending. Okay, this is a key word. Okay, because as I said, we want to find the lowest place, okay, in the cost function. So once the gradient is 0, what do we mean by gradient is 0? Okay, remember gradient is basically the first order derivative. Okay, like just differentiate the cost function. I mean, you learn that from calculus, right? Like I'm not asking you to remember like all the detail of the calculus that you are learning. I'm just asking, okay, where you can find like the gradient, the first order derivative to become 0. It's a bottom of it's at the bottom, right? Okay, where like you are the gradient, the derivative is going to be 0, right? Or you can say, oh, I mean, it could be also on the top, right? Either at the top or at the bottom. Basically, it's extreme value. It's where the extreme value happens, right? Right? Any question with that? Okay. But here, okay, I want to emphasize that it's not very likely to be the maximal value. Okay, because we start, okay, remember, I say we place the ball at the random position, at the arbitrary position. So the situation where you happen to place the ball at a maximal location is unlikely, right? But when the ball, start moving, it must move downwards, right? It must move downwards. It doesn't move upwards, right? It is against physics, right? Okay, so I mean, eventually, okay, when the gradient reaches 0, okay, most likely you reach the minimum. Okay, it's impossible. I mean, when you roll the ball, okay, and when the ball stops, it stops at the highest place of the surface. It's against the physics, right? So that's the basic idea of gradient descent. Okay, so concretely, I mean, you start by filling theta with random value. So as I said, this is called like a random initialization. So you start at any given location, okay? And then, okay, you improve it gradually, okay? When I say improve it gradually, okay, you are trying to find the direction that is going to reduce the cost function, okay? And you take baby step at a time, one baby step at a time, okay? And each step is going to bring your cost function a little bit lower, okay? And you keep doing that, okay, until the algorithm converge to a minimum, okay? So this is like the basic idea of gradient descent. Very, very important, because the same idea is going to be used, okay, in deep learning again and again. Basically, like pretty much any model training, we are going to use gradient descent, okay? So there's an important parameter in gradient descent, okay? It's the size of the step, okay? Okay, it is determined, actually the size of each step is determined by two things, not by one, okay? The first one is the slope, okay? How steep the slope is, you can imagine, okay? The steeper the slope, okay, the bigger the vector, okay, the bigger the vector, okay? And second is like this learning rate. This learning rate, okay, will be used to multiply with the vector that you obtain, okay, to tell you, I mean, you know, for each iteration, you know, where you are to end up, you are going to end up with, okay, from the previous position, okay. So this learning rate is very important, okay, as I will show you in several examples that, okay, if the learning rate is too high, okay, the result may not be, you know, it may not converge, okay, you may get a jumpy result, okay. Why is that? I will show you with the example, okay. But if the learning rate is too small, okay, you can imagine, okay, you are trying to get to the, you know, the minimum, okay, but each time you are going to take a very small step, okay, so eventually it's going to take too much time, okay, you are going to go through many iterations, okay, in order to reach the minimum, okay. So that's either either situation, I mean, will not be good, okay. So we will have to find a good learning rate value, okay. I will tell you like how we can find a good learning rate value, okay, later, okay. So not all cost function look like a nice regular ball, okay. If it's a very simple regular ball, then as you can imagine, like the ball must roll to the bottom of the ball, right? So that's like very simple, okay. But unfortunately, okay, some cost functions, okay, may look very ugly, okay. So there may be holes, okay. Holes means there are some discontinued locations, okay. But this situation does not happen very often. I just want you to be aware, okay. And the ridges, plateaus, okay. I hope you guys, I mean, you know, have no problem with these English words, okay. Basically, like you just describe all sorts of irregular terrains. Just describe different shape of terrain, okay. So this will make the convergence, okay, to minimum, okay, difficult, okay. So exactly, I mean, what difficulty are we going to face? There are two, situations that we don't want to see, okay. The first one is, okay, yeah, I mean, it converge, okay. I mean, when you roll a ball, okay, it may stop, but well, unfortunately, it may stop at the local minimum, right? I mean, when you reach a local minimum, obviously, you know, the first order derivative is also 0, right? But obviously, a local minimum is not, you know, as good as the global minimum, okay? Because normally, when you want to find the optimized solution, okay, you want to find the global optimum, not the local global minimum, not local minimum, okay? So if this happens, obviously it's not the ideal situation. So we are going to also discuss like, I mean, what you can do to get to, what should I say, like to avoid this. To be honest, this problem cannot be completely avoided. Okay, you can only mitigate it. Okay, reduce the chance this happen. This is going to happen, but it may happen. Okay, it may happen. Okay, the second one is it may take a long time to cross the plateau. Okay, I mean, if you happen to, you know, that the converge would has to go through like a long, like a plateau before it reach the local, I mean the minimum, before it reach the minimum. So that, you know, that plateau, okay, plateau basically 高原啊, okay, 高原. So I mean, in a plateau, okay, basically like the height are similar. Maybe it has a little bit slope, but the slope is very small. Okay, so because the slope is small, remember I told you there are two things that control the movement of this ball, right? The first one is turning rate. The second one is the gradient, right? Okay, the gradient. Because in the condition, in the situation of the plateau, okay, the gradient is also very small, okay, because it has similar height, okay. So it will take a long time for you to travel, okay, through the plateau to reach the minimum, okay, and a lot of time because, you know, because after all this is an iterative approach, right? So I mean sometimes you will set like a upper bound for this number of iteration. So when the program reach this upper bound, and unfortunately the ball is still in the plateau, well, so you haven't reached the local, haven't reached the minimum, right? So this is, I mean, this could happen, okay? So I'm also going to discuss like how you can try to avoid it, okay? So if I use like a two-dimensional, okay, because like on slides, I can only show you two-dimensional situation. Of course, in your mind, I really suggest you to think of it as like a three-dimensional cases, okay? But for two-dimensional situation, okay, it's kind of like you have curve. This direction is just like your feature. This is your cost function value, okay? X is your feature, Y is your cost function. So if you have one feature, okay, and you can start at any random location, and you, as I say, like you determine like which direction, okay, will give you like a smaller cost function. So in this two-dimensional situation, because it's basically it's a curve. So well, it's just like one, no, first order derivative will tell you, okay, if you travel to this direction, okay, I mean, when you increase the value of theta, if you are here, it will tell you if you increase the value of theta, it's going to give you a smaller cost function, okay? And based on this idea as well as the slope you are getting, the slope is the gradient, right? As I said, okay? Then you multiply the slope with your learning rate, and then you update your theta position from here to here. Okay, this is the, you know, the update. okay? And you can keep doing that. But you can see that, okay, actually the moving, the movement, okay, the moving like a update, it's becoming smaller and smaller, right? This reduction of the update is not caused by the learning rate. As I said, the learning rate, okay, normally, okay, at least like at the current, at the current moment, we are assuming the learning rate is fixed, okay. The reason this updated interval becoming smaller and smaller, it's because the slope becomes smaller and smaller, right? Okay, as it approach this place. So eventually, okay, when it gets to very close to the optimal solution, you can see the curve, the slope, okay, of the tangent, which is the derivative of you get for the first order derivative. It's close to zero. Okay, so this update becomes smaller and smaller. Okay, so this is like a visualization of gradient descent. Okay, when the learning rate is ideal. Okay, the learning rate is set ideal. Okay, why do I say that? Okay, this is a situation when you set the learning rate too small. It is still going to, go to the minimum, but you can see that it's going to take a much more number of iterations than this one, right? Obviously. Okay, so if you set the learning rate too small, you may have this problem. Okay, it's going to take many iterations to reach the minimum. Okay, and how about if you set the learning rate too large? Okay, assuming we are here. Okay, and you set the learning rate large, what happens is that, okay, at this place, because it tells you, well, in order to get a smaller cost function value, you should go to the, you should increase the theta value. And then that derivative, that slope, okay, will be multiplied by the learning rate. And unfortunately, in this situation, the learning rate is too big. So it goes directly to here. So at this place, okay, well, the first order derivative will tell you, okay, in order to get the smaller cost function, you should go to, you should reduce the theta value. Okay, so the slope will point to this direction. Okay, but again, because the learning rate is big, so instead of just moving a little bit closer to this place, okay, you go all the way to here, and this range is going to be bigger. Why? Because the slope at this point is bigger than the slope at this point, right? If you have a fixed learning rate, assuming that learning rate is big, okay, then the update is going to become bigger and bigger and bigger and bigger. Okay, so this is a situation when the learning rate is too large. Okay, so you also want to avoid that situation. And this is the visualization for the difficulty that I mentioned, those two difficulties that I mentioned for the gradient descent. The first one is local minimum. You can see this is a global minimum. This is local minimum. But when you roll the ball, okay, you may end up at local minimum because you don't know where you start the optimization, right? It could be any random location. So if you happen to start from the local minimum, from somewhere close to local minimum, you may, converge to a local minimum. That's the first problem I mentioned for the gradient descent. Okay. The second situation is this plateau. Okay. The converge may have to go through a long plateau, which, you know, well, it may have a little bit slope, but the slope is really not that big. So because the slope is small, so you have to, you know, go through this plateau like with many, many iterations. So, well, so it takes a long time to reach the global minimum. Okay, so these two difficulties, I mean, if you use a figure to show it, I think this is, you know, one of the visualized example. Okay. So, as I said, like, of course, like, these difficulties, okay, or like, you know, those like, you know, local minimum, global minimum, or plateau, okay, all these situations, okay, even with like, you know, remember I told you that your cost function may not be continuous, okay, or may not be differentiable. I mean, but as I said, the situation for that is not very often. But okay, remember, okay, in the case of the linear regression that we discussed, okay, what is the cost function? We assume we are using mean square MSE, right? Okay, the mean square error, okay, is our cost function, okay, for the linear regression model, okay. So mean square error is basically like your estimated y, okay, minus the true value, right? True value y square, okay, and you sum up all these things and divide it by the number of samples, which is m, okay? So because it's a simple, well, quadratic function, so it is a convex. It's a convex function, okay? We can prove that very easily. It's a convex function. What do we mean by convex function? Okay, geometrically speaking, if something is convex, it means that if you pick any 2 points on the surface and you draw a straight line, okay, between these 2 points, okay, that point, that segment, okay, the segment, okay, connecting those 2 points will never cross the curve, will never cross your convex function again. There will be no solution in the convex function. So based on this idea, okay, it actually implies that there are no local minima, just one global minimum. Okay, if you basically for a convex function, no matter how you draw it, it's going to look like something just like a ball, Okay, so it is also a continuous function with a slope that never changes abruptly, okay, because it's a quadratic form, right? And we can differentiate at any location, which is good, okay? So it's continuous, and the slope never changes abruptly. So MSE is a good cost function. I'm not saying all the cost functions look like that, but I'm saying now because we are dealing with linear regression situation, so MSE, the cost function happen to be MSE, and MSE has all these good properties, okay? So, well, so at the end, okay, it tells you that, okay, gradient descent is guaranteed to approach arbitrarily close to the global minimum for the linear regression situation, okay? If you wait long enough, and if the learning rate is not too high, okay, as long as you have these two assumptions, okay? And we know the cost function has a shape of a ball, okay? For MSE, yes, it's going to look like a shape of a ball. But it can be an elongated ball if the features have very different scales. Okay, what do we mean? what is the elongated ball? Okay, I'm a big fan of college football, but you guys probably don't know what the football is. When you guys mention football, you probably consider football as a soccer, right? 就是大学美式足球。Have you guys watched those games, or you guys at least heard of rugby, right? 橄榄球 rugby. Okay, so the ball played in rugby or college football, it looks like this shape, right? It's not round, right? It's a little bit, it looks like, that's, if you get that ball and then you try to cut it in half, okay, the shape you are getting, okay, is what we meant by elongated ball. Or if I show you a figure, it looks like this. Okay, this is the lowest place. Okay, but you can see it's here we have like we are actually trying to visualize a three-dimensional situation. Okay, so we have theta 1, theta 2. Okay, we have two features. Okay, two parameters, and the height is indicated by the color. The lighter the color, the lower. Okay, the lighter the color, the lower. So these two figures actually shows. They show like a three-dimensional situation. But unfortunately, because we have slides only. Okay, the slide can only show this three-dimensional in two-dimensional case. But we use color to show you. Okay, so this looks like a ball, right? Okay, it's just like a ball that you use to eat your rice, right? Okay, so this is like a lowest place. Okay, but the elongated ball is like this. Here we have the lowest place, or like an optimal location, but well, it's not like a round shape. It's like this shape. It looks elliptic. Okay, elliptic. Okay, that's what I meant by like if you have a ball from rugby. Okay, you cut it like in this direction, then what happens is you are going to get something like this. So this happens when you have two different, the scales of your features are very different. Okay, if the scale of theta 1 and theta 2 are very different. Okay, so okay, when you using gradient descent, okay, you should try to avoid that elongated ball situation. Okay, you should ensure that all features have similar scale. Okay, how do we do that? You can use the scikit-learn. There's a standard scalar class. Okay, we are going to talk about these things later. Okay, but anyway, like just want you to want to give you a head up. Okay, so this standard scalar class is going to normalize different features, okay, and help you to avoid elongated ball situation. But obviously, let me tell you, okay, sometimes you cannot completely avoid that. But so you may ask, so what is like why do we not want elongated ball situation? Okay, you can see like well, in the regular ball situation, okay, it converge directly toward the minimum. Okay, in the elongated ball, okay, if you have tried to, well, probably you don't have this experience, but you can imagine elongated ball, okay, and if you place a ball somewhere like here, okay, you will see that because this direction, this y direction, okay, at the y direction, like you are going to get the larger gradient, right? Because it goes down faster. And at the x, x direction, the gradient is smaller. Okay, the gradient is smaller. The y gradient, the gradient for y is larger. The gradient for x is smaller. So what happens is that, okay, it's going to go this route. Okay, at the beginning, because you have a larger y gradient, so it actually goes down faster. And then gradually, okay, when it goes to here, I mean, it gradually like, turn and then reach the minimum. So what happened is that, okay, there are two things I would like to say. First, which distance, okay, assuming you start from similar location, it's difficult to say like because it's a randomized location, but assuming you start from a similar location, okay, which distance is smaller? The left-hand side, right? Why? Because it's a straight line, right? We know straight line beats the curve, right? Okay, in terms of this, I mean, reaching a location. Okay, if you want to go there, going straight, obviously, is faster than going, detour, right? So this one, okay, because the distance is shorter, so it will converge faster, right? Okay. Second, okay, when you go this route, okay, it doesn't go in the direction of the minimum. So sometimes you can see like even like a fluctuation, like here. So it goes like actually like this, not exactly this good, okay, like this curve. It goes actually like this. Okay, so it's going to even further increase the distance. Okay, so that's why the elongated ball, okay, is not as ideal as like a regular ball. Okay, so we would like to. That's why we want to, normalize, okay, each feature to make them like at the same scale. Okay, so well. So let's take a 10 minutes break. When we come back, we will continue the discussion of the gradient descent. Okay? Okay. So now we have discussed the gradient descent concept, right? So basically, okay, here, okay, is the implementation detail, okay, to compute gradient of the cost function, okay. We know the cost function is pretty much like what should I? It's a summation y square divided by n, right? So because it's remember like here we are assuming we have like multiple features, okay? So this yi hat is actually theta 0 plus theta 1 x1 plus theta 2 x2 plus plus theta n xn. Just want you guys to remember what we have done, right? Okay, so you can plug in this yi hat in here. And then, okay, do the partial differentiation. Okay, partial differentiation, because, well, we are talking about a higher dimensional situation, so it's a partial differentiation. Okay, for any particular theta I, theta j, I mean, that's what we are going to get. When you partial differentiate theta j, okay, on this, okay, you can treat all the theta, all the other theta as constant. So all the other thetas are gone. Okay, so you are going to end up something like this. Okay, it's very, very simple form, right? So this is for particular theta j. So if you try to, because we are trying to get like the vector, the gradient vector. So what you are going to get is like you do a partial derivative for theta 1, for theta 2, for theta 3, etc. for theta n. So you have n dimension vector here. Okay, so you can rewrite it something like this. Okay, and one thing here you need to be careful about is that obviously this is like to calculate any term here, you need to get like the value from all points, all samples, right? Okay, so this complexity, okay, basically is like well, it takes m, okay, it takes m, not n. Okay, m is, remember we have two different different parameters that control the complexity. One is n. N represent the number of features. M represent number of samples, right? So here, I mean, it takes, we have to plug in m samples to obtain all these values. And well, this calculation, okay, is really like linear to the number of samples, okay? So we term this as like the gradient, okay, for the MSE, for the cost function, okay? This one actually, okay, will give us, okay, this formula just, I mean, I think I already discussed this formula, so I was, okay, but here, okay, so the algorithm, okay, as I said, like it will require you to consider all the samples, okay, to compute one gradient vector, okay. So each time it takes linear n, linear to like n samples to compute this gradient for one, for each computation, and we call this algorithm batch gradient descent because it uses the whole batch of training data, all the samples, at every iteration. Okay, so it may be a little bit slow. It may be a little bit slow, okay, because it takes all samples to determine the direction, okay. So, but you can see that gradient descent scales well with the number of features. It doesn't, care that much to number of features, okay. Training a linear regression model, when there are hundreds or thousands of features, is much faster with gradient descent than using, for example, normal equation, okay, which takes as bad as n cube high complexity, okay. So you can sort of like write the update function like this. The next location for theta is the original theta, okay, minus eta times this gradient. We already know what this is, right? This we got it from here. Okay, and eta is the learning rate. Okay, eta is the learning rate. You can see the eta times this gradient determine how much update will be taken. Okay, and it is a minus. Okay, why? Because this gradient normally indicate the direction to go up, but now we want the direction to go down, right? So we have to, basically just point to the opposite direction. That must be the direction to go down. Okay, so this is the very, very fundamental function for gradient descent. Okay? So this is like a very simple implementation of gradient descent. Okay, I will not go into detail for the programming. I think this is a very simple Python code. Okay, basically direct translate this equation into a loop. That's it. Okay, but in this loop, we set the number of iteration to be 1,000. Okay. And we try to, the learning rate is 0.1, and we try to give like a random starting point, and then we do this iteration, to do this iteratively for 1,000 times. And at the end, the theta 0 and the theta 1 is like this. If you still remember, okay, where is it? What is the value we got for a normal equation? This one, right? And the value we got for the scikit-learn function is also like this. And the value we got for the gradient descent pretty much is the same. Okay, it's the same. Okay, so which is nice. Okay, think about this. Okay, as I told you. Okay, this thing, this step takes about m, order of m. Okay, and you do this iterating for 1,000 times. Well, the iteration step is a little bit high, but well, it's a fixed value, so it doesn't change the fact that this algorithm is linear to the number of samples. Okay, so which is nice. Okay, any question? No. Okay. So this shows you the iteration, okay, of this gradient descent. And remember, I told you the learning rate matters, right? Okay, so here, okay. On the left-hand side is the situation where you have a smaller learning rate, which is 0.02. I mean, in the program, we are using 0.1. Okay, so this 0.1 learning rate actually gives us a very good convergence speed. Okay, but if you set it to be 5 times smaller, you are going to have a much slower convergence. Okay. Oh, the red line indicate the initial value for the theta. Remember, we randomly initialize the theta value. Okay. So the random initialization, we assume the same random initialization for 3 different learning rate. Okay. And this one will just give us a slow convergence. This one is good, okay, but this one, if you set the eta, okay, learning rate to be too big, okay, 5 times bigger, what happens is that original is here, and then it goes to here, and then it switches to here, and then, as remember I told you, like it's going to, oscillating, okay. Oscillating. I mean, between back and forth, going back and forth, and it's not going to converge. It's actually going to diverge. Okay, when you have when you set the learning rate too big. Okay. So here, I already explained. Okay, these 3 figures. Okay, but here, one last thing to mention. Okay, to find a good learning rate. Okay, how do we find a good learning rate? Okay, one way to do it is to use the grid search. Basically, just say okay. Say like 0.1, 0.2, 0.3, 0.4, 0.5. You can try different values and see which one works better for you. Okay, but you may want to limit the number of iterations. So when you try the grid search, maybe for each value you only set the iteration to be maybe 50. Okay, or like even like lower than 50. Okay, basically you just want to see like if it looks like it's going to converge or not. If it doesn't converge, okay, it goes like the result, if the result is very jumpy, then you know this is not this learning rate may be too big. Okay. So you don't need to really like set a very large number of iterations when you do the grid search. Okay, so you just want to eliminate models that take too long to converge. Okay, so that's pretty much like how you find the learning rate. There are other approach to find a good learning rate, and we are going to which are better than grid search, but we are going to discuss those in the next chapter. Okay, in the next chapter. As for number of iterations, okay, if it's too slow, okay, if it's too low, okay, the number of iterations is too low, so you may not be able to reach the optimal solution. Okay, the always stop before it finds the optimal solution. But if the number of iteration is too high, then you pretty much waste the time waiting for the result. Okay, because like maybe if you set it to be like 10,000, maybe after the first 100, the next 9,900 will pretty much give you the same result anyway. Okay, so you are going to just wait there and waste your time. Okay, a simple solution is set a very large number of iterations, but to interrupt it when the gradient vector becomes very small. Okay, so this is a kind of like adaptive approach. Okay, when the norm, okay, remember the gradient is a vector, right? So what we are caring about is the size of this vector. So we are checking the norm of this gradient vector. Okay, if it's smaller than a tiny value, we set it to be epsilon. Okay, we call this value called as a tolerance. If it's smaller than the tolerance, we assume, okay, we stop the gradient descent and then assume we already reached the minimum. Okay. This approach is actually sometimes, okay, in the later part, we are going to talk about a more, what should I say, a more complete version of this. Let me put it this way, okay, a more complete version of this is called like a early stop. Okay, early stop. And we are going to discuss this again, in the next chapter. Okay, not this one. Okay, but the idea is pretty much just like this. If after a couple of the iteration you don't see much improvement for the performance of the model, you can pretty much stop this training process. This is like what we call early stop, but I mean, the similar idea is already mentioned here, okay? So when the cost function is convex and the slope does not change abruptly, okay, such as the case of MSE, right? So batch gradient descent with a fixed learning rate eventually will converge to optimal solution, but it may take a while, okay? Actually, I mean, a study shows that, okay, it can take, you know, big O 1 over epsilon iterations to reach the optimal solution, okay, within a range of this epsilon, okay, which is called tolerance, right? And well, so based on this observation, say if you want to set a smaller epsilon, okay, say you want your optimal solution to be more accurate, so you set this epsilon from epsilon, original epsilon, to epsilon divided by 10, then you will expect, okay, it will take 10 times longer, 10 more, 10 times like a number of iterations to give you that accuracy. Okay, so this one just tell you, you know, there's a trade-off between the accuracy and the amount of time it takes, okay, obviously. I mean, so in the previous slide, I already talked about batch gradient descent. It basically utilized the whole sample data to determine the gradient vector, right? So now, okay, what about, you know, because of it takes the whole sample data to determine the gradient vector. So each iteration, it may take a long time, right? So what about if for each iteration, we just randomly pick one value, one instance from the sample to determine the gradient. Okay, we could do that, right? I mean, basically, okay, here, in this equation, okay, it tells you that we need to use all n value, right? But it doesn't, you know, restrict us from just using one value, right? We just assume n to be 1. We just randomly pick one one xi and yi. That's it. That's it. Okay. So we can you know basically plug in the same function here to determine the gradient vector. Okay. So if you use only one, if you use like you know, as I say, like the batch gradient descent, because each iteration take too much time. So another extreme, we just take one instance to determine the gradient vector. Okay, so this algorithm, okay, will run much faster, right? Because each iteration it only take constant time. Okay, and it also may make it possible to train on huge training set. Why? Because if we need to compute like a gradient based on the whole training set, there are situations, I mean, that the training set is so huge that you cannot load the whole training set to the computer memory. Okay, so in that case, like the batch gradient descent may be a problem because it considers the whole training set, right? But if you only consider one instance from the training set, obviously you no longer have that issue. So I mean, you know, so you don't need to worry about memory situation, okay? Regardless how big the training set is, okay? So on the other hand, okay, because you know, due to its stochastic nature, if you don't know what stochastic word is, okay, basically stochastic you just replace it as a random, okay? It's just a more fancy way to call random. Okay, so because like we randomly pick one instance, so obviously, I mean there are some there's some random nature involved in this algorithm. This algorithm is much less regular than batch gradient descent. Okay, so instead of gently decreasing until it reaches the minimum, okay, the cost function will bounce up and down, decreasing only on average. So think about this. Because your data point, okay, even though your data, your training data, okay, may have a trend, but as I already told you, the data may also contain noise, right? And those noise may make your data set, like some data may tell you to go this direction, some data set may go you to go the other direction. Okay, but of course, like if it has a certain trend, there will be more data to tell you to go that particular trend, right? But it's just like there are some, you could say that those data is outlier or something. Okay, it will tell you to go somewhere else. Okay, but so if you happen to unfortunately pick up entry that is outlier, okay, the result may be slightly jumpy, but on average, okay, statistically speaking, okay, you are going to get get closer to the optimal solution. Yes, but it's just statistically speaking, okay. But the result is still going to be a little bit jumpy. Okay, so over time it will end up very close to minimum, but once it gets there, it will still continue to bounce around. Okay, so it's going to be somewhere close to the minimum, but not exactly minimum because of its stochastic, because of its random nature. Okay, so this algorithm is called SGD. Okay, in short. Okay. So once the SGD algorithm stops, the final parameter values are good, but not necessarily optimal. Okay? So it's going to be something like that. Okay? So if you use the whole data set to find the optimal, most likely, the converge direction is going to be much smooth. However, if you only use one, okay, each iteration, if you use only one instance, what happens? That you can see what happens is going to be like statistically it's going to converge to the minimum. Yes, but you can see there are some instances that actually bring you back. Okay, those instances may be caused by the noise. Okay, so those instances may bring you back. And even when it reach this place, it is still jumpy. It is still jumpy. So no matter when you stop, okay, as I said, the solution is going to be solution you get from the SGD is going to be close to optimal solution, but not necessarily optimal solution. At least not as good as the optimal solution. Okay. So there's one advantage that the SGD has that batch gradient descent does not have. Okay, which is remember we talked about the local minimum. Okay, the local minimum is a bad situation, which because it if you use batch gradient descent, most likely because the movement is so smooth, so it's going to stay at the local minimum. Okay, you cannot escape from the local minimum pretty much. But if you use batch gradient descent, okay, because it has this jumpy nature. So the good news is that it can somehow help you to avoid being captured by the local minimum. Okay, So this is like one advantage that you may have, okay, from the SGD that you cannot have from the batch gradient descent, okay. And this is the implementation. So again, I mean, which is actually similar to the batch gradient descent. So I will not go into the detail, okay. But you can see that, okay. Here, okay, we do this thing like after 50 times, okay, this iteration only run it for 50 times, okay, and we got pretty good solution. It's 4.21, right? But 2.77, right? If I remember correctly. So this is close to the optimal solution, but not as good. Not as good. But the speed is great, right? Only 50 iterations, and remember, each iteration you only use one instance, so it's very fast. Okay, it's very fast. This algorithm, actually, if you try to investigate time complexity, well, pretty much it's just linear to the number of iterations. I mean, but the number of iterations, if you fix to 50, well, you can pretty much say this algorithm is constant time. Okay, so it is fast, it's quick. Okay, but it gives you good solution. But as I said, this is not the optimal solution. Okay, because if you compare with the optimal solution, this is not exactly like that. But even if you run this for 1,000 times, unfortunately, it doesn't give you any solution better than something like this, because it's going to be jumpy around the optimal solution anyway. So yeah, I mean, we only use 50 iteration and we get this, which is pretty nice. But if you want to improve this one, let's say I want 10,000 iteration, and I want a better solution than this one. Unfortunately, this algorithm doesn't give you that. Okay? Oh, by the way, okay, this batch gradient descent, stochastic gradient descent, all these ideas will be carried over to deep learning. Okay, that is why I talk about this. Okay, so you can see that this is like in the training. Okay, we start from the same initial location and use the stochastic gradient descent. Okay, the first 20 steps. Okay, it looks like it converges pretty fast, right? But after it reach like this area, okay, it actually like become very jumpy. Okay, around that area. Okay, so that's the nature of SGD. Okay, so one more thing to talk about, okay, is that, okay, in the SGD, by the way, I mean, just want you guys to be aware, okay, SGD has been used in deep learning very often, okay, so we want to discuss it a little bit further, okay. So in the case of SGD, okay, because each time we pick one instance in in random, okay, in random order. So some instances may be picked several times, okay, per epoch. So while others may not be picked at all. Okay, so this may make your algorithm, may make the result like the behavior not that great. Okay, so if you want to, ensure algorithm go through every instance at each epoch, so one approach is to shuffle the training set. You just shuffle the training set and then use those to do the batch gradient descent. Okay, sorry, not batch gradient descent. To do the stochastic gradient descent. Okay, you go through. After the shuffle, you go through like instance, your samples instance by instance. Okay, and shuffle it again, and so on. Okay, so this approach generally converges more slowly. Interestingly, okay, this approach actually converges more slowly. Okay. Without shuffling, without working on all this, okay, the original version of batch gradient descent actually converge faster, but well, during the convergence, it may be more jumpy. That's the issue. Okay. So another thing, when using stochastic gradient descent, the training instances must be independent and identically distributed. Okay. Statistics, we call this thing, this nature, IID, independent and identically distributed. Okay. To ensure the parameters get pulled toward the global optimum on average. Okay. So, you know, one way to ensure that is that before you run your gradient descent, okay, you shuffle the instance, okay, during the training. Okay, so, you know, this approach ensure, okay, the data you use has this IID nature, okay, very simple, just do a shuffling, okay. If you do not shuffle the instances, what happens? Okay, if the instances are sorted by label, say like you order, I know one question in like one famous question is to predict like a housing price, right? Housing price. If you try to like order the housing price in the training set, the order the training set in the ascending order or descending or whatever, okay, in the order of their house price. Okay, then you label you order the data based on the label, okay, the cost, okay, housing price. Then you use that, okay, in your SGD. The SGD will start by optimizing for one label and then the next and so on. So what happens is that, you know, SGD behavior will not settle close to a global minimum. So this is very important, okay. You want to make sure, okay, each instance you pick for SGD is selected randomly, okay. If it doesn't have that nature, okay, the result may be bad, pretty bad. Okay, so this is like you know, how you optimize, how you implement the SGD, but really you don't need to write a program for SGD. Sorry, we already have like a program written, for SGD previously, okay, here. But here we just want to tell you that, okay, actually scikit-learn has a class called SGD regressor, which pretty much does the same thing. You just use that, use the import SGD regressor, and then set up like for example, you want the iteration to be 1000, the tolerance, the epsilon, okay, you want to set like to be 10 to the power of -3, and the penalty to be none. Okay, this one is related to the tolerance. Okay, and the eta 0. This is the learning rate. Okay, so we set it to be 0.1, which is the same as the previous one. Okay, so and then you just call the fit method and on the data set, and you are going to get this one. Obviously, this is, as I say, because this is stochastic gradient descent. So every time you get you have the result. The result may be good, but not exactly optimal. Okay. So that's SGD regressor. Okay. So we have two extremes. I already discussed two extremes, right? One is batch gradient descent, okay, which use the whole data set, okay, whole training set to determine the gradient vector. Okay. The other direction is each iteration you only use one random instance from the training set to determine the gradient vector. So, you know, we a lot of us, I mean, want to do it like somewhere in the middle, right? Okay, so somewhere in the middle there's a mini batch gradient descent. What is mini batch gradient descent? Okay, basically, we know one instance, okay, even though it's randomly picked, okay, it will give us like a more jumpy result, right? But if you use the whole set, whole training set, it's slow, okay, it's slow. So in between, okay, we want to use, say, each time we use a fixed number of instances, but we randomly pick this fixed number of instances, okay? So that's like the idea of mini batch gradient descent. So at each step, so instead of computing the gradient based on a full training set, okay, or based on just one instance, okay, you know, we will, so mini batch gradient descent computes the gradients on small random sets of instances. We call these small sets as mini batches, okay? And the main advantage of mini batch gradient descent over stochastic gradient descent is that you can get a performance boost from hardware optimization of matrix operations. Because if you look at this this original batch gradient descent formula, this is actually a matrix multiplication. Okay, this is actually a matrix multiplication. But of course, if you once you reduce this thing into one instance, then, well, it's no longer matrix multiplication. So, but if you use a fixed number of instances, you still pick those instances randomly. Say like each time you use only 100 instances from the training set, and then you know, this is still going to be a matrix, and the matrix operation, okay, in many hardware, okay, there are matrix multiplication optimization that can speed up the computation actually, and additionally, okay, you know, it's more stable than the stochastic gradient descent, okay. So there are also pros and cons, okay. The algorithm's progress in parameter space is less erratic, as I said, it's more stable, okay. Not as stable as batch gradient descent. See, somewhere in between these two extremes, okay. Especially with a fairly large mini batches, okay. So as a result, mini batch gradient descent will end up working around a bit closer to a minimum than SGD. So which is nice, right? Because eventually, if you want the result to be closer to the optimal, okay, then one compromised, solution you can use is maybe the mini batch gradient descent, okay. So on the other hand, it may be harder to escape from local minima, okay, because one special advantage that comes with the stochastic gradient descent is it has the ability to escape local minimum. But now, once you use mini batch gradient descent, it is less likely to escape from local minimum. Okay, so so here shows here's a figure that shows like the convergence, like convergence of these three different approach. Okay, you can see batch gradient descent is shown, which is shown by blue line. It is very stable. Okay, it goes this direction, and then it's probably more like an elongated ball situation. So it goes this direction, and then have a small turn, and then toward I think the optimal solution is somewhere here. So this it pretty much goes, I mean, to the minimum, okay, very stably, okay. And the stochastic gradient descent is shown, which is shown in red color. I mean, you can see it's very jumpy. Even when it reach the area that is the optimal, I mean, it is still, going back and forth near this area, okay. And the third one is the mini batch, which is shown in green color. So you can see it is still jumpy a little bit, but statistically that it is not as jumpy as stochastic gradient descent, especially if you look at the situation when it reach the area of the optimal solution. Okay, it is much concentrated here than the stochastic gradient descent. Okay, so basically this figure shows you the nature of these three algorithms. Okay, to be honest with you, like batch gradient descent does not get used in the deep learning that much. We use mini batch gradient descent and the stochastic gradient descent like more often. Okay, it is because like in deep learning we have a lot of training set. Okay, if your training set is not large enough, you actually shouldn't consider deep learning anyway. Okay, so once because you have a large training set, so batch gradient descent a lot of time doesn't work well. Okay, so here, okay, we show you the comparison of algorithms for linear regression. Okay, so for normal equation and SVD, yeah, I mean they have nothing to do with number of samples in the training set. Okay, but if there are many features, if the n is large, then normal equation SVD are slow. Okay, we know that. Okay, and but for the batch gradient descent, it has nothing to do with number of features. But if you have a lot of training instances, it's going to be slow. Okay, and if you use a stochastic gradient descent or mini batch gradient descent, okay, then no matter how large your feature is or how many training instances you have in the training set, okay, your algorithm will both be very big, very fast, and but they are, in gradient descent, no matter you are talking about batch, stochastic, or mini batch gradient descent, okay, you have some parameters to decide. Okay, for example, like a number of instances in a batch, okay, or like a learning rate, those type of like hyperparameters. We call them hyperparameters that you need to consider. For normal equation SVD, you don't have that. Okay, so that's about it for all different linear regression algorithms. Okay, again, I just want to remind you. Okay, the reason I cover this is to tell you the idea of gradient descent. Okay, so then the next one I'm going to introduce is the polynomial regression. Okay, again, the reason to talk about this is really not about polynomial regression, even though we are going to talk about polynomial regression, but really the intention, okay, the intention behind this is to tell you the overfitting, underfitting, and those concepts and learning curve, all those things. Okay, so let's take 10 minutes break. When we come back, we are going to talk about this later. Okay, in our next class. Okay, so from the name of this model, you may think linear regression can only be used to deal with like you know the sample that looks like linear. Okay, but in reality, okay, linear regression can be used to you know to fit like a nonlinear data. Okay, so we can extend. Okay, we can extend the linear regression. Okay, to add the powers of each feature as new features. Okay, and then train a linear model on this extended set of features. Okay, this technique, okay, we call it polynomial regression. Okay, so of course, like to demonstrate like the polynomial regression, we first need to have a data set, right? So we try to generate some samples based on a simple quadratic equation, okay, something like this. This is obviously, you can see, it's y equal to 0.5 x squared plus x plus 2. Okay, this is a equation, but we add like some noise, okay, to make this data set a little bit random, and we generate like 100 instances. Okay, so the result look like something like this. I mean, you can probably observe that, okay, this data set, okay, there's a trend something like this, right? Okay, which actually is like you know, it should be something like similar, something close to the equation that we use to generate this data set. I mean, but obviously this data set, I mean, if you use a linear equation, it doesn't look good, right? If you try to draw a line, okay, obviously there's no straight line that can fit this set of points very well. Okay, so so straight line will never fit this data properly. Okay, so we can use polynomial feature class to transform the training data, adding the square, okay, the second degree polynomial, okay, of each feature in the training set as a new feature. Okay, now because we only have like one feature, so the square term that we add is just the square of that feature. That's it. Okay, so I mean I think like it's here we poly feature. Okay, we just use this polynomial feature class. Okay, assign degrees 2. Okay, to pretty much like include like a second degree like a feature in the training set, and then okay, pretty much like we can with that, okay, we can with that data set we can just use that data set to do a linear regression, and the result, okay, will give us like something like this. Okay, so the intercept is this, and the x0 and the x the coefficient for x and x squared are like this. So we know like a coefficient for the I mean the bias is supposed to be 2. The coefficient for x is 1. Coefficient for x squared is 0.5. So you can see that this is coefficient for x squared. It's close to 0.5. The coefficient for x is close to 1. And well, the original, the bias is 2, but now it's 1.78. So this is close to the equation that we use to generate the data. Okay, so if you draw this line, okay, this the line that we use we generate. I mean with the linear regression, okay, this quadratic equation. I mean shown on the figure looks like this. So it captures the trend of all these data points pretty well, right? Okay. However, and obviously we can use this one to do predictions, okay, in the future. But however, if we we can there are multiple features. If there are multiple features, polynomial regression is capable of finding relationships between features. Okay, so for example, if we have two features, say x1, x2, okay, and if we generalize to square, okay, now for this example we only have x, right? So the square, the second order is just x squared, okay? But if we have two features, x1, x2, then not only we introduce, by using like a polynomial class, okay, not only we introduce x1 squared, x2 squared, we also introduce x1, x2, okay? So if we say we introduce the order 3, what happens is that we are going to have x1s, say we have two features, x1, x2, then, and you said like order to be 3, then what we are going to have is x1 squared, x1 cube, x2 squared, and x2 cube, as well as x1, x2, x1 squared x, and x1, x2 squared. All these intermediate terms. Okay, polynomial regression will automatically generate all those terms for us, all the combinations of features up to a given degree. Okay, so this is like what's going to happen. But for the example, because we only have one feature, so it only generates like a x squared term, and so if you transform an array containing n features, then what you are going to get like this many features, n plus d, the factorial divided by d factorial of d. Okay, so it's going to be a times n factorial of n. So it's going to be a lot, okay, of feature that you are going to add. Okay, so beware of the combinatorial explosion of number of features. Okay, so this is like just need to be aware. Okay, it's not just going to add like just square term. It's going to add like the interactions between like different features. Okay, so if you perform high degree polynomial regression, you will likely fit the training data much better than with plain linear regression. Okay, so linear regression, it would if you don't use polynomial regression to generate like the second order, obviously it's going to generate a line, right? But that line doesn't fit very well. But if you use like if you generate like the second order, a polynomial, then it as I showed earlier, it looks much better. But how about if we use like a 300 degree polynomial model? Supposedly like the higher the degree, the better fit of the model, right? It's going to give us smaller errors, supposedly. Okay, but what happens? Let's have a look. This is a linear regression. A linear line that we are going to get with this data set. Okay, and as I previously discussed, it's not going to perform very well. This red line, and the quadratic form give us pretty nice trend of all these data set, these data points. Okay, as I already showed you earlier. Okay, but if you try to generate a 300 degree like line to fit this all these points, what you are going to get is this green line. is this green line better than the blue line? Any thoughts? How many of you think it's the green line is better than the blue line? How many of you think it's not? It's worse than the blue line? Okay. How about those who never raise a hand? You don't have opinion? Okay. I mean, I expect you guys to express your opinion. I mean, it's okay to be wrong. I mean, that's fine. Okay. But anyway, okay, yes. Okay. Let me make this very clear. Okay. In the data science, okay, regardless it's machine learning. Here we are still discussing machine learning, okay? But even though it's machine learning, okay, but even for the future, okay, we are going to talk about deep learning, okay, regardless deep learning or like some simple machine learning algorithm, okay. What we care about is the trend of the data, okay. When you see the trend of the data, obviously this quadratic form captures the trend pretty well. I mean, this blue quadratic line, okay, actually is better than the red line for no question about it. It is also better than the green line. Why? Because green line actually, if you look at the green line, it actually pick up not only the trend but also the noise. Remember, I mean, when we generate those points, we intentionally add some noise into it, right? And those noise, okay, should be considered just as background noise, white noise, because we use Gaussian distribution to add those noise, okay? They should be considered just background noise. But if you use a model with 300 degree, yeah, it not only pick up the trend, but also those noise, okay, which shouldn't be considered in the trend of the data, okay? So yeah, I mean, in this case, when the model capture not only the trend but also the noise of the data, we call this overfitting, okay? And if the model is not complicated enough to capture the trend of the data, for example, like this linear equation. This linear equation model is too simple to capture the trend of this data set. This is exactly what we say underfitting. Okay, this concept is very important. Okay, this is the reason I discuss polynomial regression. Really, polynomial regression should be covered in machine learning, which is considered as prerequisite of this class. But unfortunately, I'm not sure if, how many of you have taken the prerequisite anyway. So the reason I want to discuss this is to talk about overfitting and underfitting concept. Okay, so this high degree polynomial regression model is severely overfitting the training set, okay, while the linear model is underfitting it, okay. So if the model overfits the data, okay, another way to call it, okay, one way to call it is, well, the model is overfitting. Another way to call it is that the model does not generalize very well, okay. Okay, the model that will generalize best, okay, is the quadratic model. I mean, the other models, no matter it's overfitting or underfitting, they normally do not generalize very well, okay. So, so when you consider the complexity of your model, okay, this is something you need to put in mind, okay. In the deep learning, to be honest, okay, yeah, there are some tasks. You should determine your model based on the complexity of your task, Okay, some tasks are complicated, and or it has a it has a lot of data set, and your model should be reasonably complicated. Otherwise, your model will, you'll have problem of underfitting. Okay, but to be honest, the most of the time in the deep learning field, okay, the problem is overfitting, because it's very easy to come up with like thousands or even tens of thousands of parameters in a deep learning model, as we will discuss that in the following chapters. So when a model has so many parameters, it's easy to overfit the data set. Okay, so just want you to be aware, okay, the overfitting concept. Okay, so when the model is overfitting or underfitting, we have some issue. But the situation for underfitting, let's talk about how we can determine, how we can tell a model is overfitting or underfitting first. Okay. One way to avoid, to look at, to be able to, get an estimate of the model generalization performance, or you can say it's overfitting or not. Okay, is to use a cross validation. Basically, if you have a data set, you can break it into k sets, and to use each set to train your model, and then to see the average of the performance of the model. But this approach is normally, okay. Let me be clear. Okay, this k-fold cross validation is more suitable for the machine learning field. Okay, like for example, like the one that we talked about, like regression algorithms. Okay, but for deep learning, okay, this approach is probably not going to cut it. Okay, because in the deep learning, we a lot of time we need like a lot of data. So, and the training a lot of time takes a lot of time anyway. So, dividing the data set into k-folds, for deep learning is rare. It's rare, to be honest. Okay, but because we are talking about the ways to see if model is generalizing very well or not. So we have to cover cross validation. Another one is to look at the learning curve. Okay, so this learning curve, okay, can be used to see if a model, including the deep learning model, okay, is overfitting or not. Okay, so what happens like, okay, on the learning curve, okay, you are going to draw two lines. Okay, normally, okay, when you have a data set, you divide it into maybe like 80% of, to be a training set, and another 20%, okay, half of them to be validation set, half of them to be test set. Okay, that's normally what you do, but the percentage may vary a little bit, but it's normally like that. Okay, but anyway, okay, so when you train a model, okay, you can draw the accuracy of the training set and the accuracy of validation set. Okay, and to see if the model overfits or the model like underfits. Okay, so the y-axis represent like the performance or the accuracy. Okay, here we use RMSE. The y-axis we use the training set size. But in deep learning, a lot of time, the x-axis is like a number of iterations for the learning curve. Okay, but it could be training set size. Okay, if we are talking about machine learning model, or for deep learning, as I said, okay, we use like a number of iterations. Okay, so you can see that, okay, at the beginning, okay, the training set, okay, accuracy is very high, okay, and the validation set accuracy, goes. I mean, here, I mean, remember this is RMSE, so the higher the worse, okay, because this represents the error. So the higher the error, the worse the model, obviously, right? So at the beginning you can see, because the model is only constructed based on very few training instances, okay? So obviously the model will fit only those training instances very well, because I mean it's very unlikely that your model doesn't have the complexity to deal with maybe 2 instances, right? Your model must be able to deal with, for 2 instances you can draw a line, right? To fit those 2 instances perfectly, right? So I mean, so at the beginning you can see it's RMSE is close to 0, right? But once you have like more than a few instances, the RMSE of the training set, of course, increase. And for the validation set, because you use validation set, you are using the validation set to, do not appear. Those entries do not appear in the training iteration. So you use those to see like the performance. So obviously, like at the beginning you have the worst validation performance, but eventually when you have more and more instances for training, okay, these 2 lines should sort of like getting close and close. Okay, and in general, I'm not saying always, but most of the case, okay, the error for the validation set should be slightly higher, okay, than the error you get for the training set, because after you use training set to train the model, right? So the model, the error, okay, you estimate, from the training set should be slightly lower than error you estimate, from the validation set. Okay, so this is like the learning curve like you normally see. Okay, I think I already explained this slide. So this is like the situation where like your model, okay, this is situation where you have underfitting. Why we say it's underfitting? Because, okay, yeah, even though you don't see the problem with these 2 lines, but the RMSE, this error, is very high. Okay, it's very high. It doesn't go down. It doesn't go down. Okay, if your model is like good enough to capture the trend, supposedly you should the RMSE, yeah, these 2 lines should be close, but they should also getting lower. Okay, so this is the underfitting situation. Okay, so how about overfitting? This is the situation, okay, that we use a 10th degree polynomial model. Okay, actually we use this 10th degree polynomial to fit this this point. Not 10th degree polynomial is not like a 300 degree polynomial. So it's not as bad as this green line, but still it obviously, remember our data set was generated by the polynomial equation, right? So degree of 10 is still too much, right? It's still too much. It's still overkill. So the result is still overfitting. So in a sense, in the case of overfitting, okay, you can see because it has a degree of 10. So the first 10 instances, it's not going to give us any error for a training set because we have perfect fit for the first 10 instances. Well, the degree is 10, so we can fit the 10 instance perfectly, okay? Okay, for the training set, okay? But as the number of instances go up, okay, you can see like the RMSE actually, okay, these two lines, okay, are not getting very close, right? They are not getting very close. The RMSE actually in the training set is actually much better than you can see compared with this one. This is underfitting, remember? So we have higher RMSE result. But for the overfitting, I mean, no matter it's a training set or validation set, yeah, I mean the RMSE value is reduced. Okay, but these two lines do not, they are not getting very close. The distance here is exactly caused by the model picking up the noise. Okay, because like well, just like here, okay. I mean, supposedly because remember the validation set does not appear in the training set, right? So you can sort of treat like a validation set as a new point that's generated around this point. So you can imagine, okay, those new points must appear somewhere in this quadratic form, right? But when this curve is like something like this, okay, this 300 curve is, okay, a lot of time actually it's, when the point is close to this curve, actually you are going to get a much worse, error than this quadratic form, right? So that is the reason. That is the reason we have a worse validation error, okay, in learning curve. Okay, why we have this gap? Okay. So error on the training set is much lower than with a linear regression model and blah blah. I think I've covered all this. So you can use the learning curve to sort of determine, okay, overfitting and underfitting. When the model is overfitting, the error doesn't go down, okay, or like the accuracy doesn't go up enough. And if model is overfitting, then the training error and the validation error, like there will be a gap, okay, after the model training, which is caused by the model picking up the noise. Okay. So an important theoretical result of statistics and machine learning is the fact that model's generalization error can be expressed as a sum of three very different errors. Okay, so there are three errors, the error. Sorry. Let me put it this way. The error is caused by these three different reasons. Okay, the first one is the bias. Okay, so this part of generalization error is due to the wrong assumptions. Okay, such as assuming the data is linear when it's actually quadratic. So high bias model is most likely to underfit the training data. So this is caused by by the wrong assumption. Okay, so for example, here the first case, this is underfitting situation. This actually we are using the linear model. That's why the first two points are we don't have any error. Okay, and then goes up. So this is like we show the learning curve of the linear line. Okay, this one based on the training set and validation set. Okay, so So obviously that's the reason. I mean, the reason is caused by, we assume the data set, the trend is linear. So that's, even though, I mean, remember I told you like last week, like before you know anything with your, if you get a lot of data, okay, before you do anything, you can try to use a linear regression to fit the model. Okay, I'm not saying the linear model is always good, but supposedly you can use a linear model as like a baseline. Okay, and if something you get is worse than linear model, it's not, you shouldn't consider that. Okay, so linear model is normally what you consider first, but obviously, I mean, you could like end up having like a wrong assumption. Like actually the points are, in this case, I mean, they are generated by the quadratic equation. Okay, but so the use linear model to fit it obviously is not good enough. Okay, so that's like the first source of the error. The second source of error is a variance. So this part is due to a model excessive sensitivity to small variation in the training data. So this variance, a model with many degrees of freedom, okay, is likely to have high variance and thus overfit the training data. So for example, the overfitting is normally caused by this variance error. Okay, this gap, okay, is caused by this variance. Okay, the third one is called irreducible error. Okay, this irreducible error is due to the noisiness of the data itself. So this one, okay, look at the keyword irreducible error. You don't want to reduce this error. If you want to reduce this error, most likely you are going to end up with an overfitting model. Okay, so this is something you want to keep in mind. Okay, so the only way to get rid of this error is to do data cleansing, or data cleaning. I mean, whatever you call it. The data cleaning is one of the important research field. Okay, I had one paper on this area. Okay, that was published in like a top tier conference. Okay, so this is like one area that is like a very important area. Okay, there are still many ongoing research on this. Okay, for example, you can fix the data sources. Okay, for example, like broken sensors, detect and remove outliers. I mean, some outliers. I mean, if you know they are outliers, you can remove them safely. I mean, to reduce this irreducible error. Okay, here, okay, when I say irreducible error, I'm saying that you cannot use the model to get rid of it. It's not like you cannot use data cleansing. Okay, data cleansing, I mean, it's different thing. Okay, it's different thing. So increasing a model's complexity will typically increase its variance. So this one, if you increase the data, the complexity of the data, complexity of the model, okay, most likely will increase the variance and reduce the bias. Okay, so conversely, reducing a model's complexity increase the bias and reduce the variance. So these two, okay, overfitting and underfitting, they are trade-off to each other. Okay, but there's a balance between them. As I said, like for example, the example I show you, okay, because we know those data sets are generated by a quadratic function, right? But in reality, I mean, when you get a data set, you don't know the underlying complexity of the model should be something, should be what? I mean, you have no idea, right? So yeah, so basically there's a balance between these two. But how to find the balance? Well, you can gradually increase the complexity of the model without overfitting. Okay, if you find your model overfits, then you know like you reach like a certain, I mean your model is too complicated. Okay, but as I said, like in deep learning, okay, most of the time you are dealing with overfitting, not underfitting, because the model is has a lot of parameters in deep learning anyway. Okay, and also, okay, when your model is overfitting, there are several ways you can deal with it or mitigate this problem. Okay, such as like you know, to regularize the model. What is regularize the model? Okay, basically it's just to constrain the model. Constrain the model. Remember, the overfitting is caused by the model having too much freedom, right? Okay, so in order to avoid model having too much freedom, you can put some additional constraint to avoid overfitting. That's the basic idea. Okay, the fewer degrees of freedom it has, the model has, the harder the model will be for overfitting the data set. Okay, a simple way to regularize a polynomial model is to reduce the number of polynomial degree, obviously. Okay, but for linear model, regularization is typically achieved by constraining the weight of the model. So the following regularization technique that I'm going to discuss, okay, especially, okay, the first two, ridge regression and the lasso regression, okay, which are also called L1 and L2, have been used in many areas, not only machine learning, okay, but also deep learning. As for elastic net, I mean, well, you can treat it as like a combination of L1 and L2, okay. I mean, so they basically are used to constrain the weights, okay. So what are them? Okay, okay. So ridge regression, also called Tikhonov regularization. Okay, this is okay. You just try to add this alpha times theta I squared, summation of theta I squared times an alpha to the cost function. To the cost function. We call this L2. Okay, that 2 basically comes from these 2. Okay? So because it's a sum of squares, right? So this thing must be positive, right? This thing must be positive. Oh, by the way, alpha is also positive. Okay? So this whole term is positive. So when you add this one to the cost function, obviously the cost function increase, right? But remember, when we want to we use the gradient descent, okay, we are reducing the value of the cost function, right? So so not only we reduce the original term in the cost function, we also reduce this term, right? So reducing this term put certain constraint to these theta i's. Okay? So that's the basic idea of the ridge regularization, or L2. Okay? So this is the first one. Okay? And the second one is called well, this is like just want to give you an idea, okay? I mean, ridge regression cost function is going to be MSE plus alpha times this one. Okay, so you can see this is basically just like the original term, okay? Well, times like 0.5 times alpha. That's it. So the other one is called let me show the first. I mean the result of the ridge regularization. So depending on the value of alpha, the higher the alpha is, the more constraint it put to the theta I. Okay, because of this cost function. The higher the alpha means this term become more and more important in the cost function, right? So when you use gradient descent to reduce this cost function, okay, more constraint will be put on this term. Okay? So that's like the basic idea. So the higher the alpha, the more constraint you have for the theta I. So what is the result? The result is something like this. Okay? So for the linear situation, linear situation, where alpha increase from 0 to 100, you can see that it becomes, more, the linear equation becomes like more and more flat. Okay, what does that mean? The flatter linear equation means the slope is close to 0, right? The slope is close to 0. The slope close to 0 means what? Remember, the slope is theta 1, right? It's a coefficient for x1, right? Okay, coefficient of x is theta, right? Which is theta 1, which is the slope, basically. So when alpha is large, it will gradually reduce that theta to be closer and closer to 0. And here is a more telling example. Okay, here we are using higher order. Okay, to approximate these points. Okay, so this blue line is when alpha is 0, meaning we are not constraining. We do not put any regularization, okay, into this model. But when alpha is only 10 to the power of -5, it's a very small value. You can see what happens is that, okay, this variance, this curve become less variable, right? It becomes less variable. It becomes much smoother, right? Again, it's due to the constraint you put to the theta, okay, to all the theta terms. When alpha is 1, it's a much larger constraint. Okay, you can see it reduced to almost a linear line. Close, but not exactly, because here we still see like a rise of the equation. But you can see the equation become much smoother, right? It's this is just to show you the power, the constraint power of the ridge regularization. Okay. Well, so we can let me finish this. Okay. So as with a linear regression, we can perform ridge regression. Okay, by computing a closed form equation. Okay, or by perform the gradient descent. Okay, pros and cons are the same. Okay, so following equation shows the closed form solution. Okay, so but as I said, like we care more about the gradient descent approach because after all, we are using this for the deep learning class. So we can also show how you can write this ridge regression into the stochastic gradient descent. Okay, so yeah, you can see you just set the penalty to be L2. Remember, I told you ridge regression is another more well-known name is L2. So you just set it to be L2. So basically, you just put the ridge regression into the SGD regressor, which is a stochastic gradient descent. Remember, I told you. So basically, that's it. So another this is closed form solution. I don't think that's any different than this one anyway. Okay, so well, So that's I think we are running out of time. So that's today we finished like ridge regression. Next time I will talk about lasso. Okay, and I will also discuss like a difference between ridge and lasso. But today, I mean, unfortunately, I don't have enough time. Originally, I thought like I should be able to cover lasso and the difference between these two. But yeah, that's fine. Let's talk about this next week. Okay. Again, just want to remind you, please go to E-Class to download the first project and find your teammates as soon as possible. Okay, if you haven't done that. Okay, so any question? If no question, I will see you guys next week. Okay, and we don't have class the week after next. Okay, just want to remind you guys again on that. Okay. 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 Let's get started. So, one moment. 等一下，遥控器。Okay. So last week we talked about the gradient descent, and we talked about we use a polynomial regression to talk about the concept of regularization. Okay. So before we start today's lecture, okay. The one first thing I want to, remind you guys is that we don't have lecture next week, okay? Because I'm out of the country for student recruitment, so so the next week lecture is canceled, but it will be made up like at the end of the semester, and one more thing is that 2 days ago when I attended the International Student Office meeting for this student recruitment, okay, I was told that okay, because by the time I came back, which is next Saturday, the second coming Saturday, okay. So I still need to do like the quarantine, right? 3+4 quarantine, okay. And the school actually originally, okay, that the +4 3+4 that 4 days, I'm supposed to be able to teach classes. Previously according to school regulation, but our school just changed that, okay, to they say like okay, that 3+4, okay, the whole period including that 4 days, okay, I will not be able to come to the class in person to teach classes, okay. So as the result, okay, so first, as I told you, the lecture next week will be canceled, but the lecture in the next week, okay, will be held online, okay, according to school regulation, because actually it's 3+4. Because I came back on Saturday, so Sunday, Monday, Tuesday, because our class is Thursday, so you know, originally I didn't think I have any problem, you know, coming to the lecture, but now the school has changed their like the regulation, so I have to, you know, teach, I mean the lecture in the second coming Wednesday, by, you know, online class, okay, so. I mean, this change is like, you know, it's made to comply with school regulation. It's not like I prefer online classes. Okay, I actually prefer to come to lecture to talk to you face to face. Okay, so yeah, just want to remind you that. Okay, and also, okay, remember. Okay, I announced the first project last week, right? So whoever, I mean, that hasn't checked the e-class for the project, please do so as soon as possible. And if you have not found your teammates, okay, remember I mean, for the small projects, I mean, you need to find one teammate to form a group, okay, of 2, okay, and I think the deadline is end of this week. Is that right? When is the deadline that I announced? Eh, 助教在吗？你们记得那时候讲是 end of this week, right? This Saturday midnight, right? 是下礼拜还是这礼拜 ？Okay, sorry. So it will be next Friday. Okay, next Friday. So let me put it this way. Okay, before our next lecture. Okay, which is online, of course. But before the next lecture, I mean, I expect you guys to form a team of 2. Okay, for the project. Okay, and if you haven't done that, you know, before the deadline, the TA is going to randomly assign a teammate for you. Okay, I don't want that to happen. Okay, so I just want to remind you about this once again. Okay, so come back to our discussion on regularization. Okay, we talk about REACH regularization, which is also known as L2 regularization. Okay, the other one, which is actually well, I wouldn't say it's more famous, but I would say it's as famous as the REACH, is a Lasso regression. Okay, Lasso regularization. Eh? Oh, I think I should. Sorry. Okay. The Lasso. Okay. So compared with the Lasso, you can see that the difference is that, okay, in Lasso we pretty much add a square of all the coefficients, the sum of the square of all the coefficients as the penalty term in the cost function. That's the REACH. But for the Lasso, okay, we use the sum of the absolute value of all the coefficients. Okay, add this term as like we add this term to the cost function as a penalty. Okay, and similarly, okay, when you minimize, because our gradient descent, okay, will help us to minimize the cost function, right? So when you minimize the cost function here, okay, it's going to minimize these coefficients as well. Okay, so obviously it's also going to put a constraint on those coefficients. Okay, that is how Lasso regression, Lasso, regularization, concept, take place. Okay, so basically, you will see something similar to ridge regression. Okay, so for example, if it's a linear situation, and by the way, here this alpha obviously is a term that you can use to control how much emphasis you want to put on this regularization. You want to put on the constraint of the coefficient. Okay, the higher the alpha value, the more constraint you put to this coefficient. So you can see that, okay, as alpha value grow from 0 just means there's no regularization at all. Okay, and in that case, this blue line obviously finds the trend of all these points. Okay, this is obviously a linear model. Okay, here we are talking about linear regression, but as the alpha value increase from 0 to 0.1 to 1, you can see that, okay, the coefficient, okay, here, I mean, when I say coefficient, okay, the theta 0, the bias is not included. So that is, you can see the theta 0 is not included, the bias is not included. So that's why, okay, I mean, you will still see the bias, the bias is not going to become 0, no. But the other one, such as the coefficient for the x, which obviously represent the slope, right? The slope become smaller and smaller, and when alpha become 1, it's going to be very close to like a flat line. Okay, which means your theta value, your theta 1 value is getting close to 0 actually. Okay, so this is just to show you how much powerful this lasso regularization is. Okay, same thing can be said for the polynomial regression. So this blue line indicates like when the polynomial regression when alpha is 0, meaning there's no regularization at all. And when alpha is just 10 to the power of -7, just a very tiny value, you can see the curve becomes much smoother. Okay, much smoother. And when you set alpha to be 1, okay, it's a strong regularization. So the result is almost close to a flat line. Okay, so so just by observation, one thing you can you may observe is that lasso regularization is perhaps stronger than the ridge. Okay, because you can see for ridge, even when alpha is 10 to the -5, okay, it's still like a kind of like a curve. Much, it's much curvy than what you get, okay, with even smaller alpha value. Okay, and when alpha become 1 in lasso, it's almost a flat line. But here, when alpha is 1, the ridge, well, it is also like a much flatter, but not as flat as what you got by using lasso. Okay, but obviously, all these are controlled by alpha value, right? We have alpha value for ridge, we have alpha value for lasso. So depending on how much you put for this coefficient, as I said, the higher alpha value is, the more regularization you put to, more constraint you put to those coefficient anyway. So the importance here I want to emphasize is really not that, okay, lasso has more constraint than ridge. No. The concept here is that, okay, they actually, I already talked about this already. So the differences between ridge and the lasso is not about the power of regularization. is about, you may think they both put the constraint, and one use the sum of squares, one use the sum of absolute value. I mean, it looks like at least conceptually they don't look much different, right? I mean, they both put the constraint, right? But so what's the difference? There's a very important difference. Okay, let me show you with this figure. Okay, so this figure. Okay. Oh, by the way, I also have to tell you. Okay, one important terminology. Okay, lasso is also called L1. L1. Ridge is L2. Okay, I think this is very easy to remember because ridge is the sum of square terms, right? And lasso is the sum of absolute value, which is power of 1, obviously. Okay, so one is L1, one is L2. Okay, but here, okay, these figures actually show you the differences between lasso and the ridge. Okay, so the top. Okay, what should I say? First, I want to tell you that, okay, the x-axis and the y-axis represent two different parameters or two different features. Okay, so you have x1, x2. Okay, so for x1, x2, I mean, you have like x1 you have theta 1, right? X2 you have theta 2, right? Also, so the x coordinate represent the theta 1. Y coordinate represent the theta 2. Okay. So, so what's first? I mean, let me explain the difference between the upper row and the low. I mean, the lower row. Okay. These two figures were obtained by using ridge. These two figures were obtained by using lasso. Okay, this is the first thing I want you to know. Okay, these two are obtained by L1. These two were obtained by L2. Okay, so second thing is, so what's the difference between these two columns? Okay, this one show you, okay, when you use this column show you when you use regularization technique, okay, to do like training, what happens to the cost function? To the cost function. Remember, in cost function there are this term and this term, right? One is maybe in our particular example here, this is MSE. Okay, I mean of course depending on your problem, okay, you may have different cost function, okay, but here let's assume we use MSE. I mean for our example here we use MSE. I mean there are other cost function obviously, okay, and this is the penalty term for the regularization. Okay, obviously L1, L2 will have different penalty term here, right? Okay, so when I say the trend of the cost function, I mean the trend of the whole thing. Okay, the sum of these two terms. Okay, so here, this shows the sum of the whole cost function. Okay, so you can see that, okay, they actually traverse, okay, what should I say, like the path, I mean, looks like a little bit at least for I should say this is L1. Okay, it goes like I mean we know like the optimal location is here. So starting from a random place, it goes toward this optimal location, and gradually converge to here. But there's some fluctuations, when it converges to the optimal. Okay, and this is lasso L1. For ridge, it is much smoother. It goes almost straight. It goes almost straight to the optimal, right? Okay, but okay, this is for the cost function. But what I want you to observe is the penalty term. Okay, the penalty term. Okay, this is very interesting. Okay, because for the penalty term for L1 for lasso, it's going to be absolute value of theta 1 plus absolute value of theta 2, right? Okay, so it actually get the theta 1 and the theta 2 when you trend it. Okay, this is because penalty term. I mean when you have more and more constraint, eventually, theta 1 and theta 2 is going to getting closer and closer to 0. Okay, supposedly getting closer and closer to 0. But for L1, okay, it will reduce both theta 1 and the theta 2, okay, at the same rate. At the same rate. So you can see this reduction from here to here, it's pretty much, you have pretty much the same reduction rate for theta 1 and the theta 2, right? But when the theta 2, okay, obviously, when you start, when the starting location is here, the theta 2 is value is smaller than the theta 1 value, right? Okay, because this is this represent the origin, right? So if you just if you just assume each of these as a one unit, then 1, 2, 3, 4. So the randomized initialization location for theta 1 is 4. For theta 2 is 1, 4, 1, right? 4, 1. So after a while, you can see because they reduce at the same rate. So theta 1 will become 3, and theta 2 will be reduced to 0, right? But when theta 2 is reduced to 0, okay, well, you cannot further reduce theta 2 because that's a minimum. That's what the minimum you can get for the square for the absolute value of theta 2, right? Okay, so the theta 2, will basically, remain 0. Remains 0. But theta 1, of course, will continuously be reduced. Okay, until eventually they will reach the origin. Okay, so this is like what happens when you use L1 regularization. Okay, and on the other hand, okay, if you use ridge, the L2, okay, at the same randomized initialization location, okay, what we want to reduce is theta 1 square plus theta 2 square, right? Okay, so if you are here, theta 1 is 4, theta 2 is 1, right? I just told you, right? Theta 1 is 4, theta 2 is 1. So 4 square plus 1 square. So you have 17 square, 17, right? So you are trying to reduce this term. But when you try to reduce this term, it means you are reducing this term, right? So originally it's 17, right? Okay. So as this value gets lower and lower, what you are going to get is going to be, this obviously represents a circle, right? This represents a circle, you know, formula, right? So when you have smaller and smaller sum of of squares, what you are going to get is that, okay, you are going to, you know, go straight to the center of the circle. Okay, so yeah, theta 1 and theta 2 also gets reduced. Okay, but in L2 or in ridge, okay, whatever you call it, okay, you can see the reduction rate of theta 1 and theta 2 are different. Okay, actually theta 1 gets reduced faster than theta 2, right? And eventually, of course, they both converge to 0, right? So why do I want to emphasize this to you? Okay, so what is the, you know, the point, okay, to talk about this, you know, different convergence rate of different, you know, coefficient. Okay, let me put it this way. Okay, eventually, okay, when you use this regularization concept to constrain your model, okay, as I said, if right now we are using this for like a linear regression or polynomial regression, really we are only talking about very few coefficients, not a lot of coefficients. But in the future, when we use a deep learning model, we are going to have many parameters, many coefficients. Okay, and some models may have so many parameters such that the model becomes very heavy. When I say the model becomes very heavy, I mean like it will require a lot of computation. Okay, for example, you need a faster GPU card to run your model. Okay, a faster GPU card, or like when you try to put your model on, for example, an embedded system. Okay, because embedded systems such as like there are so many different embedded systems that for example, your phone is the most common embedded system that you carry every day, right? So, or like when you drive a car, the car, of course, even though it looks big, but it is also an embedded system. Okay, in most of those embedded systems, it has only limited computation power. Okay, so you want your model to be, what should I say, lightweight, so that your embedded system is able to execute your model. Okay, I'm not talking about linear regression. I'm not talking about polynomial regression, because as I said, these models, they are machine learning models. Majority of machine learning models are lightweight. I cannot recall any machine learning model that is heavyweight. Okay, but deep learning models are different. Okay, there are so many deep learning models. They are, very heavy. Okay, so sometimes we want to make some model lightweight. Okay, so in this if you want to achieve this goal, okay, you can also use Lasso. You can also use L1. Why? Because you can see that, okay, Lasso will first force the coefficient, smaller coefficient. It will force the smaller coefficient to 0 first, right? Lasso, for example, here, okay, remember, you can see theta 1 is 4, theta 2 is 1, right? So during the training, it actually enforce the L2 because L2 is smaller. Sorry, theta 2 is smaller. So theta 2 becomes 0, right? Theta 2 becomes 0 first, right? So I mean, well, in your model, if you are able to reduce some smaller coefficient to 0 first, then your model will not need to compute so many coefficients or so many parameters, whatever you call it. So it also means your model becomes, much more lightweight. Okay. But on the other hand, if you use L2, well, it will reduce all the terms to all the coefficients to smaller terms. But it will not eliminate any of them. It will not eliminate any of them. Okay, so L2, if you want to use L2 to reduce the size of the model, it's not likely. Okay, because you pretty much cannot get rid of any parameters, okay, by using L2. So this is a big difference. Okay, I just want to emphasize this to you. Okay, so other than the regularization, okay, power of regularization, okay, that Ridge and the Lasso bring to you. Okay, if you want to make your model lightweight, okay, L1 or Lasso is also a technique you could try to use. Okay. So, well, I already explained this. Okay. So, for Lasso regularization, because you use the sum of absolute value. So, you add this term, okay, penalty term to the cost function, and obviously this penalty term is non-differentiable when any of those theta I becomes 0, right? Because it's going to be like when you differentiate it, absolute value is like this, right? It goes down, okay, until when it reaches 0, okay, when the value is negative, it becomes positive. So it's everybody knows the absolute value, y equal to, you have this figure, right? So this point is non-differentiable, right? Okay, I'm not talking about advanced calculus. This is obvious, right? Because if you look at from the right hand side, the slope is 1. If you look from the left hand side, the slope is -1. Okay, so there's a discontinuity, okay, for the slope, okay, at the value x is 0. Okay, so or the theta I is 0. Okay, so but we have in the gradient descent, we are still be able to to deal with the discontinued points. Okay, so but I don't think you need to worry about this detail. Okay, so don't worry about this. You just need to know that, okay, even if you use Lasso, which may have a discontinued, may not be differentiable at some point, okay, the gradient descent also works for you. Okay, so this is the example of the code, okay, using Lasso class. Okay, so it's a very simple. You just specify, okay, Lasso regression, okay, and you specify the alpha value, okay, and that's it. Okay, but here this one is used, along with the I believe it's for linear regression. Okay, so eventually, we are going to talk about L1 and L2 in that can be used in the deep learning. Okay, so don't worry about this. I mean, you know. So the third one is the elastic net. Okay, elastic net is pretty much like you can treat it as a combination of ridge and lasso. Okay, so you can see it add these two terms into the cost function. So the important thing is, you know, we introduce additional gamma value here. Okay, so we multiply. This is the term for the lasso, right? We multiply this penalty term for lasso by gamma, and we multiply the penalty term for ridge, okay, by 1 minus gamma divided by 2. Okay, well, but you know, like you know, this you know, divided by 2, okay, actually, you know, is originated from the lasso, right? In the lasso, we already have this divided by 2, okay? Lasso. Oh, sorry, ridge. We have this, you know, 1 divided by 2 in the ridge originally anyway. So actually, what we got extra here in the elastic net is this 1 minus gamma. Okay, so we have gamma here. We have 1 minus gamma here. So pretty much like when gamma is 0, the elastic net becomes you know, L2. When gamma is 1, okay, this term becomes 0. Okay, so the elastic term becomes L1. Okay, so depending on the value of gamma, okay, the elastic net behaves like somewhere in between L1 and L2. Okay, so but you probably don't need to worry about this. Okay, because eventually, like in the deep learning, we don't use elastic net a lot. Okay, so this is an example of using elastic net with the linear regressions. But I just want to tell you like a regularization concept in the through this linear and polynomial regression. Okay, so last concept to cover, okay, in this set of slides is early stopping. Okay, remember, okay, the purpose to introduce regularization is to fight with overfitting, right? Okay, because when the model is overfitting, it doesn't generalize so well with the new data. Okay, so okay, there's another way you could use to fight with with overfitting, and the cost is actually very, very minor. Actually, it actually saves the time for training. It's called early stopping. Okay, let's look at this. Okay, so remember I told you, okay, the learning curve. There are a couple of ways to represent learning curve. Previously, I used like the x axis for that learning curve that I talked about. Okay, is the size of the training data. Remember? Okay, but if you remember, I told you at that time. Okay, another way to represent the learning curve is to use the number of epochs or number of iterations for the training. Okay, I mean these two are roughly equivalent because the more iteration normally means the more data you considered in the training anyway. Okay, so this represents the number of iterations. Okay, and the y-axis, as I said, okay, for the learning curve, I mean you could use either the error or accuracy, right? Okay. And here, I mean, we use RMSE, which is also one type of error, right? So you know, normally, I mean, as I said, for the training set, you are going to get a slightly lower you are going to get, lower error, okay, which is, so the RMSE for the training set is represented by red dotted line, okay, and for the validation set error, okay, is represented by blue line, okay, and remember I told you, okay, when these two lines are getting, more and more far away, that's the case when the overfitting happens. Remember? Okay, I talked about this like last week. So to be honest, okay, because you use training set for training, so it is, the training set. As more and more as you use like more and more iterations to train your model, okay, you will see, this the error for the training set gets actually reduced more and more, but at the end, it may be almost like flat, but still like it's going to be, in the worst case, it's going to be flat anyway, okay? But for the validation set, okay, and initially it goes down, but at some point of time, it becomes it may become flat. For some point at some point of time, and then eventually it's actually going to go up. That is when your model starting to pick up those noise. Okay, and that's the indication that the model becomes overfitting. Okay, so obviously, look at this figure. When should you stop model training? Should be here, right? But the issue is, you don't know. You don't know how many iterations you should stop the model training in advance. You don't know. Okay, so the early stopping concept is very simple. Okay, it just try to it just record the validation error. Okay, so this it memorized. Okay, so in the early stopping approach, basically after the training of one iteration, you first save this model. Save it because it may be the best one. Okay, you first save this model and measure the validation error. If this validation error is lower than the previous one, you pretty much remove the previous copy of the model. Just save the current copy. Okay, and then you start working on the next iteration. So the next iteration, if it doesn't improve, okay, keep in mind this, at this point it may be when even though I draw this one as like a so smooth, but actually it may have some jitters, but it may go up and down a little bit. So you may want to so you may see like in the next iteration, the validation error gets up or down a little bit. Okay, when it goes up, of course, you don't want to save this current model because, well, the performance of this model is worse than the previous iteration, right? But you need to remember, okay, this is, so you just keep working on, okay? So after, say, like after a number of iterations, say like 5 or 10, after 5 or 10 iterations, if you still cannot find a lower validation error, then you should stop your model training. Okay, you stop it, you cut it, you no longer train it. Further, and then you basically remember. You will save a copy of the best model that you have so far for the validation error, right? So you are going to record basically like restore that model back and use that as your training result. This is called early stopping. So basically, for early stopping, you are going to, it's okay to set a very, very large number for the iteration, because eventually the training will be stopped, okay, before the model run into like overfitting anyway. Okay, so you don't need to worry about like setting a large number for iterations. Okay, so early stopping, how we of course like for linear regression or the implementation, this rollback is just like we just try to get the best, the model with the best performance back. Just copy that back. That's called rollback. Okay, so don't worry about this. So this is like the implementation of early stopping on the linear regression and the polynomial regression. Okay, this is just an example for that. Okay, I believe this is for the linear regression, but for the deep learning, we have a different implementation for the early stopping. I just want to tell you the concept of early stopping, which will become very useful. In the deep learning field. Okay. Remember, like we have slang say like there's no free lunch, right? There's no free lunch. Okay, but the early stopping is a technique that you do get free lunch. Okay, because it actually tells you to stop training early, and you get better performance, right? So it's like you get better performance without sacrifice, without costing you a lot of overhead. Okay, so this is a very good technique, and this early stopping concept has been used in deep learning model training very often. Okay, so that is it for the getting started set of slides. So I will. Any question? I think it's about time for the break. So let's take 10 minutes break. When we come back, we will start the next set of slides. Where is it? Here. Okay.